probability has a really rich history, okay? And probability didn't come alone like that. In fact, probability has a very deep connection with permutation combination that you have learned in your high school days. So permutation combination have a really interesting connection with, I mean, it has an interesting rich existence. Uh, it has been seen in 1200 AD, okay? So in this pamphlet, this contains a permutation combination puzzle, okay, which actually tells nothing but it's called a Fibonacci rhyme. It's actually this is not from 1200 AD. I'm sorry, it's from 1600 BC. It's called the Rhind Papyrus. Okay, so where the it's just a poem where it's telling that, as I was going to St. Ives, I met a man with 7 wives. Each wife had 7 sacks. Each sack had 7 cats. Each cat had 7 kids. Kids, cats, and sacks and wives. How many were going to St. Ives? So this was a poem, okay? It's called a Fibonacci rhyme. So inherently, this rhyme contains, it was a puzzle, of course, and this rhyme contains the SIDS of counting permutation combination. Okay, so I will try to copy and paste this rhyme over here. Now the question is that how is probability? How is this probability related to this combinatorics? And how does probability start at all from its very basic core? How did it start? So it was around 17th century. Okay, it was 1654. So there was a French scientist. His name was Chevalier de Moret. It's a French name, and everything started from gambling. Okay, people love to gamble. People love to earn money, and naturally they lost money. People didn't want to lose money. They want to increase their chance, in quotes, of winning. So the Murray used to bet. Okay, he used to gamble a lot, and he used to bet that, in 4 rolls of die, okay, one would get at least 1/6. This was his bet. The Murray actually betted that in the gambling room, that in 4 rolls of die, at least 1/6 would turn up. He was winning consistently. And he became greedy, and he wanted to understand and made the game a bit more advanced. And he told that in 4 rolls of die, 1/6 would come up. He changed the game to that in 24 rolls of two die, not one die. So in 24 rolls of two die, a pair of sixes will come up, both. In 4 rolls of one die, understand this very carefully. In 4 rolls of one die, he told that at least 1/6 will come up. He told in 24 rolls of two die, a pair of 6 will come up. This was his bet. And he lost. He questioned that whether 24 was favorable or 25 rolls were favorable, to make the, which number of rolls are favorable. He then went to the mathematicians out there. There were Pascal and Faraday-Fermat, and they had something. They wrote a letter to each other. It was called the famous Pascal-Fermat correspondence. Okay, And there, this problem was discussed between them. They didn't have WhatsApp at that time, so they used to discuss with letters. So this was a starting point of probability. So if you consider timeline of probability around 17th, 18th century, after Pascal and Depré Formes started answering questions and solving problems in 17th, 18th century. So this is the timeline. I always share the history because it's very important to know. In the 16th, 17th century, they there was Pascal and Fermat, and then in the late of that century, there came up Jacob Bernoulli and Abraham de Morey. And they started understanding probability, and essentially they were trying to understand what it means, how to mathematically model chance, like the chance of winning. What does it mean? Like if you can't measure something, then you cannot win at it. This was the fundamental philosophy. So they wanted to measure, and measuring needs mathematics. So Bernoulli and De Morey, the De Morey was a person who on whose name the complex number ka De Morey's theorem is there. Format, I hope you know. Pascal's ka you also know. Bernoulli is the person whose Bernoulli trials you will read in the future. There were two person, Jacob Bernoulli and his son, or I mean, two Bernoullis, the father and the son were both mathematicians. Okay, so in 19th century, then there was the work of Laplace, and then there was Chebyshev, Markov, and Kolmogorov. Chebyshev, Markov, Kolmogorov, they did some more work. And then in the 1933, which was the foundation of Indian Statistical Institute, like that was where it was built. So there was a building called Kolmogorov Bhavan. Okay, if you ever go there, I hope a few of you at least will go there. So you will see there's a Kolmogorov Bhavan, and it's also the statistics and mathematics unit. So sitting in that, not in that unit, but around that place, that's why it was named Kolmogorov Bhavan. The famous axiomatic probability definition was formulated. Okay, and it's pretty interesting that there was a history created in ISI, and actually many histories are created in ISI in terms of probability and statistics. So it feels also good being a student out there, and I'm teaching you probability. So this was the entire timeline of how the probability was developed. Okay, axiomatically finally, which we will learn in depth. So this was a brief history of how probability was developed. But the next natural question is that how do we model probability? What was the starting point? Like, was there a specific starting point out there for probability? How did it actually start? So we learn that. So the starting point of probability was very simple. Okay. And in fact, we will learn there are three modes of modeling probability. Number one is called the classical approach because it's the first classical way. The next one is called frequentist approach. The final one is the axiomatic approach. And you will see that axiomatic approach actually gives back this classical and frequentist approach in some sense. We will learn that. So we will learn the classical approach today. Next week we will learn the cons of the why classical approach actually failed. And then we will learn next week, when we will learn axiomatic probability, how the frequentist approach tried to surpass the problems that classical approach face, and how what were the problems in frequentist approach, and then we will see how axiomatic approach, you know, just contains everything, and we will see how. So frequentist approach we will see also known as the law of large numbers. We will see that. So today we will understand what is a classical approach, and it was a very natural approach of defining probability, of understanding probability. So classical approach, as the name suggests, it's a very classical and natural way of defining probability. So what was the problem? Let's take a simple problem. So let's take Jacob, sorry, Chevalier de Murray's problem. He was telling that in 4 rolls of a die, at least 1 6 will come up. So this was his problem. At least 1 6 will come up. Now, if they ask, this was his bet, he wanted to be in his favor. So naturally, he want to understand what is the chance of it, which they lovingly call probability. What is the probability of this, like of this 1 6 coming up in 4 rolls of a die? And the classical approach is a very similar framework to axiomatic probability. We'll see that. But the natural thing is to do what? Is to check that what was the possibilities, all the possibilities in the 4 rolls of a die. All the possibilities, right? So all possibilities, all the possibilities. This was an experiment, okay? So the Bernoulli, what they did in the late 17th century, they tried to build up this experiment. So the experiment is 4 rolls of a die. And then they try to understand that what were the outcomes of it. Okay, the outcomes, all the outcomes. That was a set, and all the outcomes contains here 4 rolls of a die. So it can be 1, 5, 3, 4. This is one possibility. Okay, it's a set of all sets because there are 4 rolls. This is the possibilities. 1, 2, 1 6 6 7. Sorry, 6 5. These are the possibilities. So they write down all the possibilities, right? But they wanted at least 1 6 to come up. So then they turned out to something called favorable possibilities. And 1 6 coming up, at least 1 6 is 1 6 4 3 6 6 6. This is one possibility, and all these cases. And then they define that, then they define that they counted this. They counted this. So let's give it a name. It's a set omega. It's a set, right? It's a set, let's say E. So they define that probability of this is nothing but number of elements in E by number of elements in omega. Right? They defined it like this. Okay, we will see this is an extension of axiomatic probability, but in some sense, what they're trying to do is that naturally, if you have a box, an unknown box, in which you have 2 red balls 3 blue balls and 4 green balls, the chance of picking up a red ball is nothing but number of red balls, total number of balls. 2, 2, 2, 2, 1, 2, 3, 4, 9. 2 by 9. That's how they define. So the experiment was picking up one ball. All the possibilities are each of this ball, red, green, blue, okay, this wall, and favorable outcomes like red, red, green, all these possibilities are there. There was a catch here, okay, but they defined this number of favorable outcomes, okay, by total number of. So no, there's a problem here. The problem is inherent. If you observe here, if you do this, let me go to the next page. If you do the same thing, 2 red balls, I think they were whatever, let's take 3 green balls and 3 blue balls and 4 green balls. If I ask you that what is the experiment? Experiment is picking up one ball. Pick up one ball and observe its color. The next is the set of all outcomes. The outcomes are nothing but red or blue or green, right? And if they ask a favorable outcome, let's say probability it's a red, it's just 1. Like it's like this 1. So how does this match here? You understand? How does this entire thing club into this equation of this experiment? Right? If I ask you probability of red ball. So they didn't think of this actually. They didn't think of this per se directly. They didn't think about this directly. Because to them, they were dealing with gambling problems. And this type of problems didn't come up. But this is the problem to the next step of the process, that why classical probability fails. There are more examples, I will come to that, but this is one very fundamental example. This model is not working here. This model is not working here. The experiment outcomes are this. The favorable is this red out of this outcome. So it's usually 1 by 3. But you can understand it's 2 by 9. Right? You can understand this in some sense. It should be 2 by total number of cases. So how to define this scenario? How to make this scenario mathematically very strong like how to have a very strong mathematical foundation of the scenario. So this kind of problems, and other kind of problems was the end of the classical probability era. They were questioned, and that's why you see after it was the 17th century, and then it was carried on for 2 centuries, and then 19th century where the next kind of things came up, the frequent test and all those things, because Bernoulli came up, and then the Bernoulli trials came up, and all those things came up. So this was the stagnant point of probability. They couldn't approach it because they were thought the ideal scenario in classical probability is that every outcome is equally probable. You will see that how it comes up. And gambling was fine with it because every card or that kind of scenario, every place was only 1 out of all of them. So they could understand that that's one by entirely the whole thing. So that was kind of really easy to understand. But so this was the starting point of the dispute between the minds of mathematicians. So the definition of classical probability is defined as follows: that if so, this is the idea. I will just write it down. So if a game has n equally likely outcomes, out of which m outcomes correspond to winning, then the probability of winning is m by n. Simple. Okay. An extension of this can be this also, that all of them are equally out, all of them has equal outcomes, and two raids are there, which corresponds to winning, and full number of are 9. So in that sense, this also fits in there. But this framework, pick up one outcome, that does not fit. But this statement fits. So there was a certain kind of dispute. Okay. But they carried on with this idea. So the definer is a set of all equally likely outcomes of an experiment S. E is the some combination of outcomes of the experiment, and probability of that event is defined as this. So this was classical probability. Now, as you see, the definition of classical probability includes this thing: the number of elements of a set. It includes counting the number of elements of a set. And the definition of permutation, combination, and combinatorics is this: that it's a study of how to count the number of elements of a set. And therefore, the classical probability approach is boiling down to, so therefore, you have to just count the number of elements of two sets. That's it. So therefore, the classical probability is nothing but equivalent to combinatorics, which is the art of counting of number of elements of a set. That's it. Number theory is defined as the understanding the numbers, the relationship between the numbers. Combinatorics is defined as how to count the number of elements of a set. The entire theory is built on that single idea: how to count the number of elements of a set. Now, of course, there is a lot of interesting things out there. We'll learn that in a very short, short type of idea. But this is the classical probability, and why classical probability is equivalent to the permutation combination framework, the combinatorics that we'll learn now. Okay, so did you understand the entire background story and how it's? Did you understand, all of you? Write in yes if you understood. If you have doubts, please raise your hand. Did Mallory understand?
Yes, sir, I understand.
Okay. Swati and I think Jyotish, did you understand?
Yes, sir.
Very good.
Yes, sir.
So, let's see why classical probability fails a bit. I will share some examples with you. The classical probability fails in this kind of aspects, that what's the probability that a randomly selected integer is odd? If I ask you this question, why it fails? What's the probability of randomly selected integers is odd? Why it fails? Can someone tell me? Why classical probability approach cannot be done or fitted into the framework.
Sir, here we can't know total number of integers is infinite. So,
Very good. Total number of integers are infinite. So the probability will be nothing but infinity by infinity, which is not defined, right? Number of odds are infinite, but we know intuitively it's half, almost half. So classical probability is not being able to match or answer the very fundamental questions. So these are certain. So these are the notes I made. So I'm just sharing the screenshot of that. So the other questions too. That what is the probability that a randomly selected number between 0 and 1. Let's say you close your eyes and pick up a number on the table, pick up a point on the table. What is the probability that that length is less than half from the origin? Or the probability of random selected value is less than half. So this kind of like the idea of infinite by infinite case is not fitting into this classical probability model. This was the most important barrier. Also, it requires S to be finite with equal mass. That's the idea. And for example, this was a very famous thing that exists in the mindset that, if I ask you what is the probability that this will happen, you will say it will either happen or not happen. So there are two possibilities, right? And each has equal possibility. So half, 1 by, so the sample space is what? All the outcomes, it will happen or it will not happen. And the favorable outcome is what? It will happen. So therefore, it's 1 by 2, half. So how, like, it was a kind of paradox here. We will learn why it does not work. Also, you think about why it does not work. Can anyone say why it does not work like that? Why this idea will not work? Think about it. Okay, the next one. So this was the classical probability failures, the cons of classical probability.
sir, in this case, the outcomes are most probably not equally likely.
Can you come again?
So, the outcomes are not equally likely. So, or basic approximation is not working. What we are
The outcome is not equally likely. Very good. So yes, if the outcome is not equally likely, the probability of, so when we say it's 1 by 2, we are assuming that probability of life on Mars is equal to probability of no life on Mars. So we'll see why its assumption is not true. That's where the axiomatic probability comes up. And classical probability is a subset of the axiomatic probability. So now we learn, of course, how to apply classical probability. That means we learn combinatorics because it's just nothing but counting the favorable outcomes, counting a number of elements of a set. Okay, any questions at this point of time, guys? Please raise your hand or ask questions. Okay, I have a question to you. that how much, okay, so I will do a poll with you, give me a minute. How much familiarity do you have with combinatorics, a permutation combination? How much are you confident in? Depending on that, I will arrange similar probability, similar problem solving sessions. Combinatorics. But you have learned in high school, okay? A high school level only, yeah. So I will just I'm giving a poll. I'm sharing the poll with you. So we need to know the fundamental counting principles, permutation combination, circular permutation, binomial theorem, multinomial theorem, and counting the like ball and stick method. So please participate in the poll, guys. Okay, so fine. So let's try to understand what is combinatorics. So as I told, it's nothing more than understanding or counting the the number of elements in a set. So you have a set A, just count the number of elements of it. So what's the big deal? What's a very big deal in it? So if you try to understand more, you will see that the idea of counting sets, just like linear algebra that you have learned, it's not just restricted to sets, but it's trying to understand that if you have two sets A and B, how do they interact? And based on the interaction, if you know the number of elements of these two sets, when they interact to give a new set C, how does the number of elements of the set dependent upon A and B number of elements of the set? So let me give an example. So first let's start with the set of all sets or collection of all sets. Let's call it C. So the question is that if you take two sets, how can they interact with each other to give rise to another set, and how it will be defined? See, that means what is the algebra of sets? When they say algebra, okay, it means that there was algebra of limits, algebra of continuous functions in mathematics course, right? We have taught. Similarly, what is the algebra of sets? How do the sets interact with each other to create new sets? For example, how do vectors interact with each other to create new vectors? That was the algebra of vector space, the axioms of vector space. And that's where the combinatorics begin. The combinatorics is studying that if you know the number of elements of set A and the number of elements of set B, how do they interact? Like based on the interaction type, what will be the number of elements of C? Now, of course, A and B giving rise to C. So how is the number of elements of C dependent on A, B, and star? That's the idea they're trying to focus on. So what are there are two fundamentals. Operations or algebra on sets, or one set or multiple sets. Can you name them? What are two fundamental operations on sets? Any idea? How can two sets interact with each other? What are the operations you know? Tell me.
Union and intersection.
Okay, union, intersection, anything else? Not only on two sets, it can be on one set also. What are the other operations you know? Give me all the operations you know.
The subset.
Subset.
A minus B.
A minus B. What are the others? There are a lot of them. Tell me.
A cross B.
A cross B, others. What can be done on one set?
Set complement.
Complement. Okay, good.
A complement. Okay.
What others? Any others you know?
Power set.
Good, good, good. Power set is one of them. Just give me a minute. So the next question is that. Okay, let me drink some water. There is something in my. Cardinality, how many elements in there? I didn't get you. Okay.
Like, yeah, am I audible?
Yeah, you're audible.
Yeah, like how many elements are there in that set? That is called as cardinality, right? I'm
Yeah,
not sure.
that's what we are trying to find. Yes.
Yeah, okay.
So yeah, all of you are right. A has this many operations. More than that, there are other things called differencing operations. So when they try to understand that under each of these operations, if we know the number of elements of A and number of elements of B, what will be the number of elements of A union B? or A intersection B, or A minus B, or A cross B, or others, power set of A. These are the kind of questions mathematicians wanted to understand. And this led to the whole theory of combinatorics. What they showed was that out of this, only two operations are fundamental. One is union, not even union, there's a different type of union. And another is this. Others are all byproduct of it. Others are all byproduct of it. We'll see how. So they told that one such example is this, that fundamental operations on set number one, not union, but it's called disjoint union. I'll tell you what disjoint union. It looks like this. Dot inside. And the final is cross product. Not cross product, cross. That A cross B. The question is that how? Why or why? Like give me an example. Why others can be constructed from here? Very simple. We will see that that's one example is De Morgan's law. I hope you remember De Morgan's law. De Morgan's law says that A union B or A intersection B, let's say we don't know this, right? Then we want to count the element of this. So it's nothing but, its complement is nothing but A complement union B complement. So we know in some sense union ka idea. If we can find the union, we know that if we know the complement of individual sets, then we can find the complement of this. So what is the complement? Complement is nothing but you have a bigger set. This is the number of elements you must be knowing. And you have a smaller set. The complement is defined to be outside of that. And that is nothing but this. So it's same as the disjoint union. So what does the disjoint union say? So I hope all of you know the cross of two sets. Do you know the cross of two sets, guys? The set of all it's this, it's A comma B, such that A belongs to A and B belongs to B. It's like a vector of elements of A and from one element from A and one element from B. That's the definition of cross product. So, so therefore, what is the disjoint union? So what does the theorem say? What are the fundamental principles? The principles are very simple. So once you visualize this disjoint union, it's nothing but similar to one axiom of probability. So if you have two sets and they are disjoint, and if you have set M here and N here, then the number of elements of this set intersection, this is a disjoint union because A and B are disjoint, is nothing but number of elements of set A plus number of elements of set B is M plus N. So this was this is called the addition principle. And there was called the multiplication principle. So what is A cross B? If you try to visualize A cross B, it's like this. Let's say you have 4 elements here and you have 2 elements here. It's it's a vector, right? So you can visualize it. How? Let's say I have 1, 2, 3, 4 is this set, and 3, 4 is this set. So if you do A cross B, you get this element is nothing but 1, 3. This is nothing but 2, 3. So therefore, all these elements of this rectangle is the number of elements of this set. And you can see it's nothing but, it's a rectangle. A cross B is nothing but a rectangle. So its number of elements of this rectangle is nothing but the length of this into length of this. That is dot A times B. So the number of elements of A cross B is nothing but number of elements of A and number of elements of B. Mathematicians told that, let's say if you, so you know that A byproduct of this is what? Why complement can be got? Because complement, disjoint union of A is nothing but the entire set S. So number of elements of complement of A plus number of elements of A is the number of elements of S that we already know. So therefore, to know this, we can subtract this. That is the complement counting. So we can know complement. We can count the number of elements of a complement. Therefore, by De Morgan's law, we can also count the number of elements of A intersection B, because we know union, we know complement, disjoint union, right? Now, how to know union from there? It's very simple. So if you want to do union, you take this set, and the common set and add it up. They're all disjoint. The idea is therefore, if you take any two sets and try to take union, intersection, and in that same plane, you will find out that you can always find it using this disjoint union if it's in the same plane, not by a cross product. In that same plane, you can find it by disjoint union. Okay, so I will give you a 2 minutes break. You find out and try to think of problems that come to your mind. Any other questions except Sucheta's one? The idea is this, that using intersection, using union, how can you find out other cases? Okay, the difference between disjoint union and union is this, that when we say union, we take between any two sets. When we say disjoint union, it's between only two disjoint sets, union of two disjoint sets, Sucheta. Did you understand? So when you have two sets, they may not be disjoint, but you can break it up into disjoint sets and then take their disjoint union. For example, if you take this to any set, if they had some intersection or some common parts, so you break it up into this disjoint ones, and you add up the disjoint and disjoint parts to find the union. So ideally, you can find out any set using the disjoint union, the number of elements of a set, if you know the entire set in some sense. Cross product I'm coming later on. So you are breaking it up every set into any set into breaking up into all those parts, subparts of it. For example, it's called principle of inclusion exclusion. You will find out that it's very simple. You already know that in high school maybe, that if you have two sets, and if you take the A union B number of elements, you can easily understand is number of elements of A plus number of elements of B. That means we are counting the number of elements of the entire this two sets union. So we first do this, then we do this. So when you add this two, you see this part is extra. Green part is counted twice. So we subtract the intersection part. So see, it's nothing but three intersections. A union B को you have broken it up into three intersections. This part, which is nothing but A minus B, that is A minus the B part, disjoint union, B minus the A part, disjoint union, there's this part, disjoint union, the green part. A intersection B. So when you add it up, you have this plus this plus this. Now observe that A minus B and A intersection B forms A. This two forms A, and if you add another this will form B. So you subtract this to, to cancel it. So you get A plus B minus A. This is the application of basic algebra and this disjoint union part to form any other set, number of elements of a set. So do we basically consider A intersection B as another set? Yes, it's a different set, right, Dhruv? It's a different set, right? So when we can find another set, so it's like we are interacting two sets to form another set. We're trying to find the number of elements in that set. That's the goal, right? That's the final goal. How do we do that? Using those two fundamental operations and the fundamental principles related to that operation. That's it. The fundamental principles are what? The addition principle and the multiplication principle. Any doubts till this point of time, guys? All of you understood this? So disjoint union is basically intersection of two disjoint sets. You're right, because the union of two sets can be written as disjoint union of some other set, like I have shown here. Okay, clear? All of you? Yeah, SK.
So I got what you told, but I'm not getting why disjoint union is intersection of two disjoint sets. Won't
Wait,
intersection of
wait.
intersection? Yeah,
Disjoint union is the intersection of two disjoint sets?
it can't be right
Right, yeah.
because it
But
will be nothing. I mean, null set, nothing in common.
yeah, but we are not taking a disjoint intersection of two disjoint sets. We are saying that we can express any other set as disjoint union of some sets.
Yeah, okay, fine.
So that's what we are saying, and hence, since it's a disjoint union, we can find those sets and add it up.
Yeah,
That's what the goal is.
okay. No, I read something in chat box and got a bit confused.
Okay. Okay, all of you clear with this, guys? Write an yes if you understood. If you have questions, please raise your hand. Okay. Did Bala, did you understand?
Yes, I understand.
Great. So now let's try to understand. So this is the two fundamental principles. Now, why the cross product came up? The cross product is nothing but adding one other dimension of sets. So this disjoint union can actually collect in the same plane, but when we add another dimension, A cross B, that the cross product helps. So how to visualize this? And that's where the tree diagram comes. The diagrams will always help human beings to understand things better. For example, if you're from physics, there are Feynman diagrams, okay, in the history of physics, in quantum mechanics, for which I'm sorry, like for the quantum mechanics for which the Richard Feynman was awarded Nobel Prize in Physics, right? So he used something called this Feynman diagrams to understand the steps of electrons or quantum particles. Similarly, diagrams helps us to visualize. And this two fundamental ideas, principles can be visualized by the diagrams. Since every problem can be tackled by these two principles. Okay. And you will see in the later part of our course how conditional probability, you will see that when we generalize this, since it's a classical probability, right? This combinatorics, we'll see that this is nothing but one of the axioms of probability. And you'll see this multiplication principle is nothing but conditional probability. They're just like the classical versions of it. These are all connected. And you will see that permutation combination is nothing but a conditional probability in approach. It's just a conditional probability, very simple stuff. So, let's try to understand tree diagrams. So, what is a tree diagram? So, if I ask you that very simple question, that it's a very simple question though. You have done it many times before. That let's say you're eating at some Emily's restaurant, and the waiter informs you that there are two choices for appetizers: soup or juice, three for main course, a meat, a fish, and a vegetable dish, and two for dessert, ice cream or cake. So, how many choices of meal for a complete meal do you have? How do you count those? So, two choices for appetizers: soup or juice, three for main course, meat, fish, or vegetable dish, two for dessert, ice cream or cake. So, it can be easily drawn by a tree diagram. In fact, tree diagram is nothing but another form of multiplication principle. So, you have soup or juice. For each soup, we have meat, fish, vegetable, meat, fish, vegetable. In each of this, we have ice cream cake, ice cream cake, ice cream cake. Each of them is nothing but, you see, this is a point in the 3D plane. In fact, in the 3D plane, if you make, here you make the appetizer, here you make the main course. On the z-axis, you make the result, each point is each of them is a point. Let's say appetizer में you have soup juice, you have meat, fish, vegetable, and इसमें there are two options. So this point here is this first point. So there are 8 points. Like how many points? 3 into 6, 3 into 2 for the rectangle here, and into 2, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 possibilities are there. It's nothing but the cross product. Why? You can express this as for each soup. So you can express this as number of soup times number of meat times the ice cream. This is how I express it, the entire set of menu, the each complete meal, you can express that in this format, right? This is the tree diagram. And how this tree diagram is helping you in, because you cannot always visualize this in 3D, right? So this tree diagram actually helps you to understand that what is exactly going on. So we will do an updated version of tree diagram in probability. That's a different thing. But the tree diagrams actually capture the multidimensional factor of this multiplication principle. Okay. I hope all of you understood this, guys. Because you cannot visualize in 3D, so they made a tree diagram format of that. All of you understood this, guys? Yes or no?
Sure.
Yeah.
So you just said that the cross product of two sets is related to conditional probability. So can you please another time explain it?
Yeah, I will explain that when I will explain permutation. Okay.
Okay, sir.
I will explain that. Yeah. Great. So now let's consider a simple problem of addition principle and multiplication principle. Let's say you have A, B, C, D. So from A to C, you have 4 flights. From C to D, you have 5 flights. From A to B, you have 7 flights. From B to D, you have 9 flights. So how many flights are there from A to D? That's the question. And directly from A to D, there are 3 flights. So the question is that how many flights are there from A to D? Anyone who wants to answer? Raise your hand. All the possibilities of flights. Anyone who wants to answer this? Please raise your hand. Yeah, Dipmallo.
Yeah, it is 90.
Okay, how do you explain that?
So from A to C, we can go we can go 4 way, and for each 4 way there are also 5 ways,
Yeah.
and A to 3 we can go directly 3 ways.
So how do you explain this using the, we are counting the number of elements of a set, right? How do you explain this? How do you, write this set down? So ideally, you will do in that way, but I'm just telling you how do you connect it to this to addition principle and multiplication principle. How do you go to the very core of it so that you understand it? Okay. So this is how it happens. First is the addition principle steps. So when you see this partition idea, okay, is nothing but 3 disjoint paths and 3 disjoint sets idea. This partition path is 3 disjoint sets. So this can be counted as, the number of elements can be counted as number of flights from A to D directly plus number of, they're disjoint, right? Number of flights from A to C and then to D. I'll make it shorter. Plus number of flights from A to B and then to D. And these are disjoint, right? These three are disjoint sets. None of them overlaps with one another. So they are adding it up. Now, we know this is 3, but how to go from A to C to D? This is nothing but number of flights from A to C cross number of flights from C to D. And this is nothing but number of flights from A to B cross number of flights from B to D. It's an AND, right? So this idea of addition principle and multiplication principle is nothing but, in a linguistic, is nothing but, this is OR. So this means this or this or this path. That means set A or set B. This disjoint union is OR union is OR idea. And cross product is AND. That means A to C and C to D both must happen together, otherwise it will not happen. The set will not exist. A to C and C to D. And therefore you can write it as 3 plus A to C times C to D, number of ways, plus A to B times B to D. And this we got 3 plus 4 into 5 plus 7 into 9. Also understood this, how the addition principle and multiplication principle are playing roles here. Yeah. Yeah, SK.
Sir, by or means exclusive or, right? I mean, either in this or in that, but not in both.
Or means actually this or this, which that may contain, this or that, any one of them. So it
Yeah,
includes,
but not in both.
no, it can include in both also. If I say that the set of all people of, who are, okay, so some of the people from here have already given IIT JAM or ISI passed this year. So the set of people who have given exam this year, or the set of people who will give the exam next year. Okay, it includes both of them, right?
Hmm.
So it has
Okay.
some intersection.
Okay.
So or means A union B. That means it can contain, it is included in A union B set. The region
Yeah.
that.
Okay. So it is not the disjoint union. Okay.
No, it's not a disjoint union. Union means or. Disjoint union is a subpart of or actually. That's the idea. It's
Yeah.
a special case of or.
So in that case, it will be like people who have given exam this year, but those who won't be giving exam next year, or sorry, ulta, those who are giving exam next year, but they haven't given it this year. That would be disjoint set, no?
No, disjoint is not. So when you say disjoint union, it depends on the set, okay, not on the operation. So you have to take two sets, like these two sets are not disjoint. So disjoint will not ever come into the picture. It's like you can only, if the union, so if you take the union for two disjoint sets, that's the disjoint union of those sets. Okay. So you can never take a disjoint union of two non-disjoint sets.
Okay.
Yeah, I mean, it's in the linguistic actually. I mean, we can only write this if these two are disjoint. We can never write this if these two are not disjoint. Okay. But you can express A union B as disjoint union of two sets, like you told. A union B minus A disjoint union of B minus A, like that.
Yeah. Okay, got it.
So, but that's not the same definition. Okay, so all of you understood this, I guess. Yeah. How we applied this problem to this. So the entire combinatorics is applying these two sets side by side. Okay. And interestingly, if you try to understand that why, Deepmalla asked me why cross product is like this, product is related to conditional probability. It's simple. The number of ways to go from A to C via C is number of ways you go from C to D, given number of ways you have come to C. Okay. Number of ways you have gone from A to C to D is a number of ways you will go from C to D, given you have reached C, times the number of ways you will go from A to C. Now, these two are actually not related to each other, but we will see that these two will be related when it's permutation. This will be related to each other. So this is nothing but this, because these two are disjoint. So we get the multiplication. You see that? Another.
Yes, sir.
So this is nothing but the probability, conditional probability coming up. If you know conditional probability, if you don't know, you can avoid this idea. This is a fundamental, okay? This is the most fundamental thing. So therefore, everything you see, every combinatorics problem can be reduced down to this disjoint union and cross product. So now, what's about permutation? So the next part is permutation. So we will do permutation, combination, and binomial theorem, and multinomial theorem maybe. And next day also we will be doing problems on tomorrow, and on Thursday Debargo will be doing past year problems on combinatorics and classical probability. It will be just counting of sets. So permutation, combination, binomial, multinomial theorem. Permutation. It's just asking this question that how many ways are there to arrange m distinct objects in n places. Why m distinct? Because if all of them are same, there's only one way of expressing. Imagine m copies, 5 copies of you arranged, or let's say they're m twins, they're exactly the same. How to arrange the m twins? Like, okay, let's forget the m twins. There are 5 red balls. How to arrange them in 7 places? There's only one way. All of them will be red. So m distinct objects. How many ways are there? So how to come? Now you have to change this and combine this. 1 second. Sorry. So to combine this and this ideas, this language, to form a set. These elements you have to find out. The m distinct objects in n places. So how to find that? That's what I try to do with the tree diagram. So you have m places. Let's try to do it. Let's say m to be 3 and n to be 5. So there are 5 places. So M distinct objects are three distinct. Okay, I think we have done. This is a bit. This will be more than this. We can actually, yeah, this will be more than this. Oh, am I wrong? Just give me a minute. I'm doing something. Yeah. I mean, you can take subparts of them. Okay. So there are three places. You have 5 objects. Okay. So you can number it 1, 2, 3, 4, 5. 5 objects. Distinct 5 objects. They are numbers and 5 places. How to arrange them in these 3 places? The question is to combine the like it is not done usually in school. I don't know why, but they just do the problem, but they don't combine it to the basic fundamentals. I realized this when I taught, school children out there. So the 5 objects and 3 places. Now the number of elements is nothing but it's asking the following, count the number of elements of the following set. So imagine this is nothing but it's a set A, B, C, such that A belongs to like A, B, C, this all set belongs to this set, all of them, but A, B, C are disjoint, are distinct. They are not same. This is what they're trying to count. If they were not disjoint, if this disjoint condition was not there, it would have been just A cross B cross C, right? It would be just now the number of elements of this. A cross A cross A. And that's where it comes like 5 options for here, 5 options for here, 5 options for here. So 5 into 5 into 5. That means this. That means it's number of elements of this set whole to the power 3. That's where the 5 cube comes up. 5 for here. For each of them 5, we have 5 options for there. For each of them we have 5. That's when we say this, it's actually counting that tree diagram wala idea. 5 for here. For each of them 5 there. So it's nothing but the counting the, it's like it's going to 2 dimension now, and then the next one will go to the 3 dimensions. That's the idea. But it's asking that this condition is there actually. This condition is not there actually. I mean, this is not cut, it actually exists. So what will we do then? Then that's where the conditional probability idea comes up. I mean, conditional probability will not idea will come up, but it's actually counting the number of elements of a set. So understand, they are distinct, right? So what they did is that for the first place, there are 5 options. 1, 2, 3, 4, 5. But for this, we have 2, 3, 4, 5. For this, we have 1, 3, 4, 5. For each of them, 5 options. 4 options then. And then for each one of them, we have 1, 2, and then the 3 options. The idea is that they can be expressed as therefore in this way. The thing that comes up very, very easy out here is that for each one of them, the next one number of elements are the same. Here 4, here 4, here 4, here 4. So it's actually it's this set. The next set you cannot actually count, but it's actually equivalent to a set which has 4 elements. This has 4 elements, it has 3 elements. It's equivalent to a set. But for each one of them, it's like actually it's counting, it's partitioning all of them into this disjoint and adding it up in some sense. That's the idea. It's like it cannot be expressed as a cross product of something. Why? Because the cross product involves just direct cross product. But here it's something else. If you try to draw the diagram of the first level only, here is 1, 2, 3, 4, 5. For 1, you will not select this, but you will select here is 1, 2, 3, 4, 5 again. So for 1, you will not select this. You will just select this. This is out. For 2, you will just select this. Sorry. This diagonal is not there. This diagonal is not there. So there actually it's counting this minus this diagonal. That's why n into n minus 1 is coming up. N square minus n, the diagonal. N into n minus 1. And then for each one of this, then minus 2 is coming up. But it's hard to count like that, right? You see, it can be arranged into this. It can be arranged into this A cross B minus this set. So every problem can be arranged into this format. But for easier understanding, they give a conditional approach. That's why the conditional probability is important. Given that first one is selected, the next one has, so given that you have something has reached here A will not be there. And then B will not be there. That's the idea. A will not be there, B will not be there. So you can write this as, I mean, that's the basic idea. A will not be there and B will not be there in the next one. So n, 5 options for here. Given that this element is there are 4 options here. And given that these 2 elements are there are 3 options there. It's essentially this diagram. This times each others are 4 elements, but not the same exact set. So you cannot write it as A cross B cross C, okay? You cannot write like that. But it's the idea is similar to that. That's how the conditional probability comes up. And this. So 3, 4, 5 times 4 times 3. Okay. All of you understood this basic idea? This idea of formulation. I think you not have been given this dimension of thought before. But did you understand, all of you? Any doubts?
So please explain this diagram again of A cross B.
This one.
Yes, sir.
So understand just the first level, okay? That how to arrange these 5 elements in 2 places. So first place के लिए two options, 5 options are there. Second place के लिए 5 options are there. But observe, if the first place में this one person has set, the next place the one person will not be occupied. 1, this place will never be occupied by the second position. This person can never occupy the second position. So this is not there. Similarly, if in the first position 2 has set, in the second position 2 cannot sit. Similarly, in third position, if 3 has already, in the first position, if 3 have already sat, the 3 cannot sit in the second position. That means they are disjoint. That means we are calculating this A cross B minus this diagonal. This is n squared minus n. That is n into n minus 1 is coming up. But we don't do like that. That's a complicated one, right? Because we cannot visualize the higher dimension. So what we do in the conditional approach. We should not say conditional probability, but conditional approach. That first step, there are 5 options. For each of the second step, there are 4 options. For each, they are disjoint, distinct, because one के लिए you have 2, 3, 4, 5, but 2 के लिए it's not 2, 3, 4, 5. It's 1, 3, 4, 5. But the number of elements are same. We can count it like that. The number of elements are same. So given that there's one element in the first place, that element cannot sit in the second place. So there are 4 options that. That's the conditional probability approach. So your first place here, first place when there are 5 options. Given that the first place has been occupied by some person, the second place can be occupied, the 4 options are there because already one person occupied in the first place. So for each one of them, there are 4 options here. And for each total, given that it has the first and the second place are occupied by 2 persons, then the third place can be occupied by 3 persons only. So that's why it's like, this is nothing but, you can write it as this permitting m elements, so it can be written as m, m elements, m distinct objects in n places. So mpn is nothing but arranging. So it's like arranging is like number of possibility in first place. This is the first. This is total number of objects m times. Now first place has been occupied. So number of possibility in the second place given that first place has been occupied times the number of possibility in third place given 1 and 2 has been occupied. You will see a similar thing coming up in multiplicative theorem of probability. Okay, so it's m minus 1, and given this two are occupied, it's m minus 2, and this will carry on till m minus n plus 1. All of you understood this, guys? Yes or no? Did you understand, Swati? So we remember like this, not the previous way.
Yes, sir. Thank you.
Okay, all of you understood, please write yes or no. If you don't understand, please raise your hand if you have a doubt. Deepmala, did you understand how conditional probability and this permutation
Yes,
is
sir,
related?
understood.
Very good. So now, this is permutation combination. You can see that this comes up to be permutation. This comes up to be m factorial by n factorial. You can easily understand this. The next part is combination. So understand that instead of arranging, they're asking that it's the same thing. Instead of arranging, they're asking the number of elements of this set. The number of sets, not the arrangement. There ABC matters, but here ABC does not matter. Such that ABC belongs to that 1, 2, 3, 4, 5, and ABC are distinct. Sorry. So there the order matters. So in PM, it was this A, comma B, comma C. It's a set. Such that this thing. But here the set matters, not the order. The idea is very simple. For every such set, understand this carefully. For every such set, there are exactly, how many arrangements are there? For every given, if you fix the elements, how many arrangements are there? M factorial arrangements, right? Because 3 options here, 2 options here, 1 option here. So M factorial arrangements are there of ABC. A, B, C, B, A, C, B, all these things. M factorial arrangements are there. For each one of them, therefore, if you do it in general framework, for each such set, there are n places, right? For each such set, it's a fixed number of elements. You have n factorial what? You have n factorial. Okay, I think I did a mistake here. It's not n, it's m minus n. Yeah, because it's m minus n plus 1. So you multiply m minus n to get m factorial. So for each such fixed set, let's say 1, 3, 5, you have exactly 3 factorial array ordered set. 1, 5, 3, 5, 3, 1. Factorial for each set. So the total number of Mila ke, we know all such cases ke liye we have MPN, number of elements, such ordered set. But each 6 such groups correspond to one such set in NCM, MCN. So each group corresponds to one such set. Each group corresponds to one such set. So if you divide by this 3 factorial, which is n factorial here, you will get therefore the NCM. All of you understood this, guys? Yes or no? If no, please ask your doubt. Yeah, SK.
Sir, I didn't get the last part. Why it is P MPN by n factorial? I didn't get that. Can you please repeat?
On the right hand side, all the ordered places, all the ordered sets are there. Okay. Now, 3 factorials is ordered sets, n factorial for n equal to 3. Each like 1, 3, 5, 1, 5, 3, this group corresponding to exactly one such unordered set, which is the NCM part. Each such n factorial group corresponding to one such set. So the total set is NPN. Each such group corresponding to one such. So if you divide by n factorial, therefore you will get number of such arrangements, like number of such choices of sets.
Because as we are choosing, the order doesn't matter. So that divided by n factorial is the correction factor. Can I say that?
Yeah.
It's a kind of correction factor to just choose and not to arrange.
Yes, because each such n factorial groups corresponding to one such choice of a set. So therefore, we divide by
So
n.
we are over counting it 3 factorial times.
Yeah, multiplying 3, yeah, in some sense. Yeah. So therefore, NCN, we know that it's m factorial by m minus n factorial. So we get added n factorial here to get this. This is the NCN. All of you, all others understood this, guys? Yes or no? Swati, did you understand? Sucheta, Vaishnav, Shreya, Shinjini, Soumya, Neha, Kruti, Kaushik, Jyotish, Ishwar, Dhruv,
So
Dipal.
not the last part.
Okay, please tell me. So don't hesitate to ask doubts, Swati, okay? Can you tell me which part you didn't understand?
So I understood that for each such subset like 1, 3, 5, there will be n factorial choices. But how are we computing this formula for MCN? I'm stuck there. I can't.
NCM means such unordered sets, all the possible unordered set, right? So
Yes.
yeah, let me explain it to you in a better way. So this is NPN. Okay, let's take so 3 elements are there, 2 places are there. Okay. So there's 1, 2, there's 2, 1, 1, 3, 3, 1, 2, 3, 3, 2. This is all the 3 P2 sets. But observe, we want to arrange them 1, 2, 3, like two elements, arrange 3 elements in 2 places. Sorry, select 2 elements, 2 places for these 3 objects. So they can sit in this set, right? This way. So observe that this group correspond to this arrangement. This group correspond to this arrangement. And this group correspond to this arrangement. So if the total number npn is there, each group the size is n factorial. So number of elements here is nothing but total number of such boxes. Total number of boxes times number of elements in each such box, which is n factorial. It's nothing but arrangements, all the arrangements, is equal to nothing but this mpn. The total number of boxes is exactly nothing but each of the arrangement, each box corresponds to one arrangement. This is nothing but ncm. Did you understand now?
Yes, sir.
Are you sure? Please don't like, please ask a doubt if you have a doubt. Okay, don't back off.
Yes, sir.
Sure you understand?
Yes.
Okay. So this is the basic idea. How like each box corresponds to that thing. So that's why it's divided like that. This is how the combination part is calculated. Okay. So we are left with binomial theorem and multinomial theorem, which we'll do tomorrow. Okay, and something else also. But you should go and revise today. You should go back and revise today how the basics of your high school combinatorics. Okay. So I initially thought of not doing the combinatorics part, but I thought of doing, otherwise you will not be able to catch up. So you should go back and read the high school mathematics combinatorics from the book of Blitzstein first chapter. Okay. You can also read Sheldon-Ross first chapter, whatever you like. So read the Sheldon-Ross first chapter. I will come back again doing the binomial theorem and stuff. So read the Sheldon-Ross, the Blitzstein first chapter. Let me show you if. Let me show you this. If you go here, go to chapter 1. Try to read this. Read everything, whatever I have told. You can find something extra also. A naive definition. Then the multiplication rule that we have told here. Tree diagram stuff. So try to understand each of this problem, okay? Because these are hard stuff, so you cannot like really try to think about this. Because I cannot really repeat these things which have been done in school. So try to think. We will start on the binomial coefficient, but if you can read it till the end, it's great. It's really easy. It's not very hard. So before section 1.5, we will be doing this during this week. The naive definition the next week comes up. So we will do this in this week till 1.5. So think about it and read it. Okay. This is important. Yeah. Okay. Any doubts, guys? Any other questions? So next day, that is tomorrow, I will be doing the binomial theorem and multinomial theorem. We will be using this idea. Do problems from permutation combination. That's very important. We will be doing problem solving on Thursday on permutation combination. Okay. And do ask doubts, guys. Otherwise, you will fall back behind. Okay. It's okay if others don't understand. Maybe you are brave enough to ask your doubts. Others are not. So be a leader in your own world. Okay. That's the suggestion. And ask doubts. Okay. That's not a problem at all. So yeah. Any other questions and queries, guys? Otherwise, I will dissolve the class today. Okay, thank you guys, and I will see you tomorrow. Bye. Today's plan is the following that we will be doing. So we have already done, I think, is Jyotish here. So Jyotish, I hope you have gone through the video, and I don't know. He told that.
Yes, I have gone through the video.
Okay, great. I hope everything is clear with every
Yes.
today's
Yes.
class. So today our plan is the following, that we will be doing some problems from the basic, till commutation combination. Tomorrow also, Vargo will be doing problems. And then we are doing the binomial theorem. Not the binomial distribution, but the theorem. Multinomial theorem. And the ball and stick method. So this is today's plan as of now. So let's start. So this will be done in 4 parts, 4 intervals. Okay. So let's start doing some problems. So let's not waste this place, and let's do some problems. So problem 1. So it's a very basic, these are basic problems that you all know maybe, but what I will do is that I will help you solve it with the help of the basic results that you already know. Okay. So one such problem is counting the number of subsets. Okay. Let's say a set 1 to the n. So how to count the number of subsets of that n set S? It's a pretty straightforward problem, but how to do with the corresponding examples, the way of doing that. I mean the algorithms that you know. So I mean the basic principles. So you have to do it using the sets, but this becomes very, don't write like this per se, but it should be a habit in you. You should know how it's happening without doing it very algorithmically. So you should know that we're actually counting a set. So how to count each set? The idea is the following, that you can count it in 2 different ways. So method 1. Is that you can partition like by the number of such subsets. Let's say this set, so n is, you're counting n is the number of, let's say A, such that A is a subset of S. This is the number of elements of n you want to count. Number of elements of n. This is the mathematical representation. So now observe that n, you can write it as disjoint union like this. A0, that A0 is a subset of S. Disjoint union of A1. We don't write this, okay? When we do problems, we don't write, we write this in language. Actually, we are doing this essentially. So this should be N. Where AK is a subset of S. The number of elements of AK is K. So number of, if a set contains 5 elements, it cannot contain any other elements, right? Number of elements. So this is the number of all 0 element subsets. This is the number of all 1 element subsets. This is the number of n element subsets. Union of all of them. Disjoint union. Okay. They are disjoint union. So therefore, you can add it up. Number of n, you can add it up. Summation of k from 0 to n, ak, ak below subset of S. Number of elements of this. Now, if that's now how therefore it's summation of k from 0. So how to select the number? How many such k element subsets are there? It's same as how many ways you can arrange, how many ways to select or choose k elements out of n sets. It's same as number of ways to choose k elements out of n element subsets, right? Did you understand this step, guys? Did you understand this step? So we are doing disjoint union. This step we are doing it by addition principle. Why? Because the disjoint union. And this step we are doing by, just by understanding the whole thing. All of you understood this, guys? This step? Yes or no? No? Please raise your hand if you don't understand. Which part you didn't understand? Anyone? Yeah, tell me. Yeah.
Yeah, the second step. Uh, I'm not sure if I've got the second step. Like, what is AK? Like, if I consider a small subset, then it can have multiple elements, right? I'm not getting what exactly is AK.
K element subsets. K element subsets. For example, if you take n equal to 3, A0 just contains 0 element, 5. A1 contains all
Okay.
ones. All
Okay, it'll be like uh.
n element contains 1, 2,
Okay,
3.
okay,
This set.
okay, got it, got it.
2 element subsets contain 1, 2, 2, 3, all those.
Okay, so we are. This is kind of listing and then counting, right?
No, we are not listing. We are actually making a disjoint unions of certain sets we can count. We are making disjoint unions of sets we can count. So why we are using this? Because we are trying to reduce something that we know. So if we take this set, we can count this set number of k element subsets out of a bigger set. How? Because if k element subsets is nothing but choosing k elements from n elements, all those n elements.
Right. Okay, got it.
So this is nothing but n choose k. So actually it's all boiling down to knowing, representing in things in formats that you all know. Others must be having some doubts. Please don't be shy, okay? If you become shy, you will not get into ISI or IIT, never. Please ask your doubts. Did you understand this, yes or no?
Actually, we are choosing this now.
I am not. Can you come again?
We are choosing k elements from the n.
Which step you're talking about? Number 1, number 2.
Ak equals k. Second step.
This is a field.
Second step. Second step.
Okay. This step.
Yes, yes.
So it's disjoint union. All of them are disjoint union because a k element subset cannot be a 5 element subset cannot be a 6 element subset, right? So all these are disjoint subsets. All these are disjoint sets. So this is a set of all 0 element subsets. This is a set of all 1 element subsets. This is a set of all n element subsets. Similarly, this is a set of all k element subsets. Did you understand, Jyotish?
Okay, okay.
Sure?
Yes.
100%?
90%.
Okay, that's not called sure. That's called confused.
Little. Can you explain once more then?
Sure.
From the, if you can explain once more from the second step or
Set of all subsets of, let's say, 1, 2, 3. Okay? Set of all subsets. That is n. इसका set of all subsets 5 है. This है. And this है. So this is A0. This set. This set is A1. This set is A2. This set is A3. The set of all subsets of this, which are 0 element. The set of all subsets of this, which is 1 element. The set of all subsets of this, which have 2 elements. The set of all subsets of this, which has 3 elements. Now we are counting each one of them. It's a set of all, it's a number of ways to choose 0 elements out of 3 elements. So it's 3 choose 0. The number of ways of choosing to 1 element out of 3 elements. It's 3 choose 1. Choosing 1 element out of 3 elements. We have done this. 3C1. It's 3C0. Choosing 2 elements out of 3 elements. This. Choosing 3 elements out of 3 elements. So 3C3. So now these are disjoint sets. So by addition principle, this sum n, this summation of all these modulus of AI, not AI actually, it should be a set of all, I mean, each of this is a AI. So yeah, I can call this B0 actually. Let's say. B0 is a set of all A0s. So it's, did you understand Jyotish now?
yes, yes, sure.
Good. So therefore it's nothing but summation of n c k, n choose k. Now that is a very big formula. There exists shorter formula from, I will do binomial theorem, then you will understand that. But let's do another way of doing that. Let's observe another way of doing that. Let's do another way. So essentially the goal is to, boil into something or make into a scenario or transform into a scenario where you can easily compute those things. Okay, that's it. It needs practice. Okay, it needs practice. You should go back to your high school mathematics course in book and solve problems from there to regain your knowledge, because otherwise you will not be able to solve the classical probability, which is the easiest of all the topics. Method 2. Now imagine we are trying to count this, right? Set of all subsets such that set of all subsets of S. The idea is that you can actually represent a subset of S in a different way. So any subset of S, let's say you have 1, 2, 3. So let's say S is equal to this. So any subset A, let's say 1, 4, 5, can be represented as, a sequence where if you consider a sequence 5 length ka vector, where the first one, so this one is 0 if this element is not there in the set, and 1 if this element is there in the set. So here 1 is there, so it's 1. In this position, you will put 0 if 2 is there, if 2 is not there, and 1 if 2 is there. 2 is not there in A. So we are putting 0. 3 is not there, 0. 4 is there, 1. 5 is there, 1. It's like kind of decimal representation of this set. Okay. So therefore, observe every set has a unique decimal number, unique decimal representation, unique this vector. You get me another set. Let's say 1, 2, 3, 5. It's equivalent to 1, 1, 1 because all of them are there. 4 is not there, so 0, 5 is 1, like on the fifth place. So therefore, every such set has a unique representation, subset. So therefore, and every such subset contain, for example, if you take one subset 1, 0, 1, 1, 0, this represents to, it's a it's a bijection. Its representation is same as what 1 is there and 3 is there and 4 is there. So therefore, counting the number of such sets is not something also same as counting the number of such A, B, C, D, E tuples such that A, B, C, D, E are either 0 or 1. So therefore, you can model this and model this whole scenario in this case, in this way. It's equivalent to this. The number of elements of this is same as number of elements of this is same as number of elements of this. So now observe that you can write this as therefore a multiplication problem. It's a cross product. You can easily see that A has 2 options, B has 2 options, C has 2 options, D has 2 options, E has 2 options. So it's product of this 0, 1 set times 0, 1 set. So it's multiplication problem 5 times. Multiplication principle. So it's 2 to the power 5. Similarly, if there are n sets, there will be n tuples. So it will be 2 to the power n. So you got a formula out here that n choose 1, n choose 0 plus n choose 1 plus dot 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 n choose n, which you have got from that side, method 1, is same as method 2. So you have got 2 to the power n. We will prove it in a different way later on. This is what we have got from this. So it's really exciting when you compare things out here like this. Did you understand the method to all of you guys? Right? Yes or no? If no, please raise your hand. I will explain it to you. Jyotish, did you understand? Very good. Great. Super. Tanushree, very good. Great. So this is the basic idea. Let's do another similar kind of thing. So now it's asked to count the number of such subsets. Now what if I ask you to count the number of two subsets, the pair of subsets A and B, pair of subsets, remember. such that A of pair of subsets of number of A comma B such that A is a subset of B and B is a subset of 1, 2, 3. A is a subset of B is a subset of this, right? It is count the number of such A and B such that this, so it's like the pair of subsets such that A is a subset of B and B is a subset of this. So how many such subsets are there? How many such elements are there? All of you understood the problem, guys? All of you understood it, guys? Yes or no?
So are we counting the number of subsets or are we counting the number of elements in that subset?
So we are counting the number of tuples of such pairs, number of such pairs of subsets of this, such that A is a subset of B. So you take, for example, the pair 1, 2, 3, 1, 2, 3, 5 is such an element here. Okay, but 1, 2 and 1, 5 is not such an element. Why? Because A is not a subset of B. There's a pair of such subsets. They're counting the pair of such subsets, all such pairs of subsets. Did you understand, Swati?
Yes, sir.
Sure? Sure?
Yes.
Good. See, I will tell you something. It's very important, okay? You may be shy enough and you may not ask your doubt. Number one, you're wasting your time. Number two, you're fooling yourself. You can fool me, you can fool anyone else in this class, but don't fool yourself. That's the silliest thing to do, okay? So if you have doubts, I'm willing to explain it to you once again, okay? So don't be shy, okay? Because remember that you may be confident enough to ask the doubt. Many people have the same doubt and they're not asking. So yeah, so you're a leader you're actually above the other mindset. So that's good. If you have doubts, do stop me and ask me. Okay, that's very important. And raise your hand. Okay, so it's counting such tuples of subsets such that A is a subset of B. Okay, so how to approach this? You can do it in many different ways. You can do it in the same choosing and all these things, but this idea of bijection and creating a new story out of the whole thing is the most beautiful idea. So imagine this is the S. Okay, this is the S, the entire S. So you are first select a B out here, and then you will select a A out here. It's in some sense it's conditional. Okay, if you know conditional probability, you will feel that there is a connection. Given that you know B, then it's easier to capture A, right? Given that you know B, it's easier to capture A. It's in some sense conditional probability idea if you have that knowledge, but we will not do that in that way. So what we will do is essentially understand selecting A and B is nothing but selecting how many ways you can select this region and how many ways you can select this region. For example, and this region. I mean, if you select this region already selected, right? Because from the rest of them. So understand, let's say this one, this set A and B. You can write it as A is a subset of B. So observe that if you select this A and B in these two, next first you select A. First you select A. Okay. and then you select the B minus A, this part. What is extra there in B that is not in A? That is 5. Once you select that, you see that what is there in S, the entire set, but not in B, is this part. This is number 1, this is number 2, this is number 3. That is what? If it's 1, 2, 3, 4, 5, the entire S, that will be 4. This is just one way of selecting that. How many other ways? A lot of other ways to select this. Many other ways to select this. Right? How many other ways to select this, guys? Any ideas? So, it's actually other way around. Imagine when I was asking you to select a subset, you had two partitions. Why the 2 was coming? 2 was coming before because this was a set A, the subset, and this was the entire set. 2 was coming because an element out there, each element out there had an option to go in here or outside that set. It is either in the subset A or not in the subset A. Similarly, 2 has either an option to be in the subset A, not be in the subset A. N has the option to be in the subset A, not in the subset A. All of them are multiplied because one is not affecting the other. Similarly, here, any element 1, if you take 1, the element 1, it will either be in this region, either be in A, or be in B minus A, or it will be outside this B and inside S. Each element has therefore 3 options. Therefore, you can code it as 0, 1, and 2, or 1, 2, and 3, whatever. Here you can code it as 1 and 0. That means if it's there here, it's 1. If it's not there, it's 0. Similarly, if it's there in just A, these are all disjoint regions, right? So they have 3 options. An element must be there in one of them at least. Exactly one of them. So which one of them? It has 3 options. Either A or B minus A here or outside this. 3 options. Right? So how can you, so therefore it's equivalent to what? So the total number of ways to make such subsets are what? So each element has 3 options. So it's same as number of such A1 into AN, such subsets, such elements. So we are coding it, right? For example, let's take an example. This 1, 2, 3 example only. A to be this, B minus A to be, the extra part is in B, not in A, because A is a subset of B to be this. And S minus B, that is not in A and B, is 4. How can you color code it? Like, not color code, but code it. So therefore, it's a tuple, 1, 2, 3, 4, 5 tuple. So 1 is there in A, so we code it as 1. 2 is there in A, we code it as 2, or 1. 3 is there in A, we code it as 1. But 4 is not there in A, not there in B. It's outside this, so it's coded as 3. And 5 is there in B, so it's coded as 2. It's in this 2 region. So this is the coding. Similarly, every such arrangement has similar such coding. So therefore, total number of such cases, total number of such subsets, such arrangements is nothing but equivalent to. So this set, let's say W, is equivalent to the number of elements such sets is equivalent to number of such tuples A1 dot AN, such that all AI either belong to 1, 2, or 3. 1 means it's either in A, it's in A. 2 means it's in not in A but in B. And 3 means it's not in A, not in B, but in the rest of the portion. So therefore, this A comma B tuple, selecting this A comma B tuple with this can be transformed into a different story altogether, which you can compute easily. That's the goal. It's almost like Sandler's theorem, okay, where you have to compare the both hand sides. It's like similar here. You have to transfer into something that you know. Sandler's theorem was it's a transfer into something on the limits where you can actually compute the limits and therefore tell something. Similarly, it's here. You can compute it easily, so therefore you're transforming it here. And it's some practice, an art actually. So this is nothing but what? It's nothing but 1, 2, 3 elements, so it's 3 to the power n. Total number of such tuples is 3 to the power n. Yeah. Did you understand, all of you? If not, please ask me the doubt. All of you understood it? If not, please ask me. Yeah, SK.
Yeah. So if we consider A as 1, 2, 3 and B as 1, 2, 3, 5, then are we whatever we have done, are we taking the care of the fact
Can you repeat the sets once again?
the A and B which we have written only, that only.
Yeah, okay.
Yeah. So if we write them as B, comma A,
B comma
then
A.
then will that be in W? No, right? That
That,
won't that pair won't be in W, right?
yeah, the vectors are different, but the number of elements will be same. It's like saying how the set of all pairs is that the set of all pairs of um, man comma woman in the world. It's same as set of all pairs of woman comma man. Not the same, but the number of elements is same, right?
Yeah. Okay. So that is also okay, right? I mean, it can be A comma B or B comma.
Yeah, the number of elements is same, but the exact mathematical equivalence of the set is not same. Mathematically, their sets are not same. The number of elements are same because the renaming of that.
Then that won't disturb the total number of elements in the set.
I didn't get you.
Like if we are saying that B is also included, sorry, B comma A is also that pair is that those kind of pairs are also included in W.
No, those kind of pairs are not included in W. I told that if you consider the set V such that it's B comma A and this condition is same, that set is not equal, but the number of elements of the set are equal.
Okay.
Yeah. Any other doubts? Jyotish, did you understand?
Yes, sir.
Swati, did you
Sure.
understand?
Yes, sir.
Very good. Okay, all of you understood? Great. I hope you understood. If you have doubts, I mean, I'm just worried about the new people out here. Okay, Moitro, did you understand? Moitro?
Yes, sir.
Yeah, I'm because what about the new people, because this old people are actually accustomed with the whole process of how we teach. So that's why I'm sure they will be asking me doubts if they have. Okay, so this is one such problem. Let's see, therefore, let's see. Just give me a minute. Yeah, Sucheta?
So, what if we try to do this problem the way we have done method 1 in previous problem? What will happen then?
Okay, so I will show that to you. So that will be a big longer one. That's why I tried this. So let's try to do it in the method 1. Thank you, Sujata, for asking me to do this. The method 1. So the method 1. So understand, you have to select A comma B pair such that A is a subset of B, is a subset of 1, 2, 3 or n. Let's call this n. So therefore, in method one was what? It's not a very definite method. You have to understand. Okay. So you have to, you know, camouflage to the corresponding problem and do that problem, okay, accordingly. So method one was based on the size of the samples of the subsets, right? Just based on the size of the subset. So yes. So the idea is that understand how to select using method one. How to select such a pair. You have an entire subset A, this N, S. First you select B, right? First you select B, a subset of this. Let's say 1, 3, 5, 7. And then you select a subset A, all possible subsets. So for this set, you get all possible subsets out here. That is 2 to the power 4. For this set, you get all possible subsets. Similarly, you can take all the subsets out there. 1, 3, 7, 1, 2, 7, 9, 10. For this, you will get 2 to the power 5 subsets. And similarly, you first select B, fix that B. It's like you will learn there's an interesting result called law of probability. First, you select B. It's like probability of A is, or any random variable X. You will find out probability of X given B is equal to something times probability of B is equal to A. Summation over all A. Okay, this text. It's nothing but so you select for B is equal to how many sets for number one elements. But okay, so okay, I will do that properly now after this. But understand that if you count like this, there's an overcounting. Why? In when you count this 2 to the power 4, it also contains a set 1, 7. And here also when you count 2 to the power 5, it also contains a set 1, 7. So it's an overcounting. So fixing B first and then finding the set of all the A's within which is inside B is not a good choice. It's not a good way of doing. One second.
But wouldn't that be an unique pair though? I mean, 1 comma 7 with the B is a 4 set subset, right? So
Yeah,
that pair would still be unique.
very good. So the pair will stay unique. So, very good. Thank you. So the pair will stay unique. They told this will be unique. So now, can you count like this?
Yes, we can, I mean, fix any particular number, say 5,
Mm-hmm.
5 element subsets. Let's say
Very
we
good.
take for B. Then there are NC 5 ways to do that. And for each of these subsets, we have 2 to the power 5 ways of making subsets out of those.
Yeah, please go ahead. Please go ahead. I'm just writing in the solution what you're telling.
So, then the thing becomes for the 5 element subsets, the thing becomes 2 to the power 5 times NC5. And for like any general k element subset, it becomes 2 to the power k times nck, and then we sum it over k to 1, k from 0 to n. And by the binomials theorem, we'll see that it comes out to be 3 to the power n.
Very good. cap is just okay. Just 1 minute, okay. Okay, can you hear me? Yeah. I hope you can hear me. Can you write yes or no? Can someone talk? Anubhav, can you just want to talk? Oh, unmute yours.
Yeah.
Okay.
Hello. Yeah.
Yeah. Okay. Thank you. So first select the zero element subsets and set all select 5. One element subsets. Can you mute yourself?
Yeah, I'm trying 1 second.
Okay, I will mute you. Maybe. Yeah. Thank you. So one element subsets are all one. Each of the one element. This is a selection of B. Okay, you can see this. 2 and all this. This is a set of selections of B. The two element subsets are 1, 2, 2, 3, 1, 7, 1, 10, 9, 5. All the two element subsets. Each of them is a B. Each of them is B. Remember that. Each of them is B. Each one of them is B. So, and then for each one of them, if it's a zero element subset, it's 2 to the power 0. If it's a one element subset, it's 2 to the power 1. If it's a k element subset, for that it's 2 to the power k. Selections of A. So it's a unique pair, you can see that. Selection of A. This is a selection of B, this is a selection of A. So therefore, it's in some sense summation of number of ways you can select B times the number of ways you can select A given you select B. Right? Where the sum is over B is a k element subset. B is k element. And there's all another summation for k. K is 0. Okay. So first you select a k element subset. There's only, yeah. I hope I've done it correctly. I'll write it again. I'll write it properly. So it's number of ways to select a k element subset. This is the selection of a B, of a single B. Okay. For every such selection, there is a B subset. Times, given that B, how many ways to select A? 2 to the power number of ways to select A. Given you have selected B. So it's number of A given that you have selected B. Okay. Here, number of ways of selecting B. You can say k element B. Bk. You can say Bk. So this is the total number of ways of selecting A and B pairs, where B is a k element subset. This is nothing but n choose k, and this is nothing but 2 to the power k. Therefore, total set is nothing but select over k is 0 to n. Number of ways of choosing k element subset of B, and then choosing A subsets of B, the subset A of B, given that you have selected B. So this is nothing but n choose k, but this is what 2 to the power k, right? So therefore it's summation over 2 to the power k n choose k from 0 to n. Did you understand, all of you, this solution? Sucheta, did you understand? All of you
So,
understood?
so can you explain this tree diagram again?
Sure. Understand this very carefully. I wish there was an option where I could select and just drop it. So you want to select A comma B pair, right? So first you select BK, not B, yeah, the K element subsets, the K element B0, okay, B1, B2, BK. So now once you've selected B0, understand that there are many ways of selecting B0, okay? N choose 0 ways, N choose 1 ways, N choose 2 dot, N choose K. See, this box contains many such B's, okay? But understand, for each of such B's, you can select, for each of such B's, you can select exactly the same number of A's. A given BK, A given B0. This box of A's. Given that B0, you can select such. So you, for there it is 5, so it's A given 5, that will be 2 to the power 0. But given that B0, you can select some number of A's. For here, there are many elements out here. For example, here there are many elements of B. But given one B, it's exactly the same number, NAB. That's why you have divided into this way, so that you can count it easily. And this is how the multiplication thing is coming up. This times this, this times this. That's how the multiplication thing is coming up. This tree diagram is nothing but a good way of multiplication principle, or viewing multiplication principle. So each one of them contains this A given B, okay? Each one of them. So here it's A given B2. Remember, for different B0, you get different this set. But the number is same, which is exactly because we are counting the numbers, not the exact set. We're counting the numbers. So given this B0, exactly the same. So it's now how many ways you can choose this B0? It's N choose K. How many ways you can choose the K element subset? N choose K. Now given you have selected, now these are all the set of B0s. Now given you have selected that B0, one B0, how many ways? So it's like N choose K dots are here, okay? Now for each dot, each such B0 or BK, you can select A given BK, number of such subsets, that is 2 to the power K. Right. So therefore, to select such A comma B pair, you first select the K element subset. Number of ways of doing that is N choose K. Now for each of the K element subset, you can choose the A, that is 2 to the power K. So it's for one, so therefore it's each such partition is this, the pair of A comma K element subsets, where A is a subset of that BK. All these are partitions. All this is the addition principle times the multiplication principle. You will see that The addition principle and multiplication together when they are combined like this is called law of total probability. We'll see that. It's a classical version of that. You can say law of total combinatorics. So we'll see the same. So we are adding the partitioning it, and then each partition is a conditional part. It's like it's a multiplication principle. Each partition is a multiplication. So therefore we sum it up over all k. Did you understand? All of you, Swati, did you understand?
Yes, sir.
Sure?
Yes.
Good. Okay, Jyotish, did you understand? All of you understood this, guys? Preeti, did you understand? Great. So I think we are good with all such the revision of this the idea of the combinatorics and multiplication generalization principle. You will be able to learn those. Please read the book, okay? That's very important. So then comes the binomial theorem. Just telling that simple stuff. If you have two variables x and y and do whole to the power n, it's same as x plus y times x plus y times x plus y. Observe, if you break it up, there will be x. So let's do it for n. X plus 3 whole cube. We'll see x plus y times x plus y times x plus y. It's x square plus twice xy plus y squared times x plus y. If you do that, you will see x cube plus 3x square y plus 3y xy square plus y cube. The question is, when we expand that, it will be x to the power n, something times x to the power n, some coefficient, plus some coefficient times x to the power n minus 1 times y, plus dot some coefficient of x to the power k times y to the power n minus k, plus dot some coefficient times x y to the power n minus 1 plus some coefficient times y to the power n. The binomial theorem, the goal of binomial theorem is to find and understand these coefficients. So this coefficient has something to do with counting the number of elements of a set. Let's say that. So when you expand that, it's just like, you will see, it's just like the coding thing, okay? So when you expand this, understand this very carefully. Let's name this, okay? Let's do it for 3. Let's call it x1, y1. Let's call it x2, y2. Let's call it x3, y3. Instead of doing this, okay, just make them distinct. Then you will see the whole thing. When you do this, you will see it's x1, x2 plus x1, y2 plus y1, x2 plus y1, y2 times x3 plus y3. You will get x1, x2, x3 plus x1, y2, x3 plus y1, x2, x3 plus y1, y2, x3 plus x1, x2, y3 plus x1, y2, y3 plus y1, x2, y3 plus y1, y2, y3. Now let's see which contributes to what. This contributes to x's cube. When you put all xi's to be equal, this contributes to x's cube. This contributes to be x square y. This contributes to x square y. This contributes to y square x. This contributes to x square y. This contributes to xy square. This contributes to xy square. This contributes to y cube. Now observe that what exactly is happening. Just give me a minute, okay? One Amazon delivery is coming. Yeah, so observe that x's cube y. So all these things, observe that what exactly is happening. It's nothing but 1, 2, 3. Here it's so observe nothing. It's not 1, 2, 3 actually, but it's actually what is happening. For x square y, here x is coming from 1 and 3, and y is coming from 2. Here x is coming from 2 and 3, and y is coming from 1. Here x is coming from 1 and 2, and y is coming from 3. Essentially, what is happening? It's selecting the number of such x square y is nothing but if you consider this as beans 1, 2, 3, from which bean you're actually collecting that x, the two x's. This 2x we are collecting from which bean? Once you collect x from that bean, automatically the y will be collected from the other beans. Oh. So therefore, the idea is that
Excuse me.
yeah.
So can you please repeat that step again? The
Yeah,
bean step.
sure. Just give me a minute, okay? Actually, one of my relatives is also coming, so he is actually calling me. Sorry for the disturbance, guys. Let me repeat it once again. Did you understand this first thing? There's all this exercise part. Before the part I'm rubbing it off. The x1, x2, x3s. Did you understand this, guys? Who asked this out?
Me, sir. Swati.
Yeah. So did you understand till this point?
Yes.
So the next thing is that the question is that how many x square y's are there? So observe that the first x square y is coming where? If you just observe it, here the three x's are coming from the x's, all the x's are coming from 1, 2, 3. It's like when you're multiplying, actually what is happening, from each one of them either x is coming or y is coming. So the degree is 3. So either x is coming or y is coming for each one of them. So which is coming actually? So when all the three x's are coming, it's x cube. When two x's are coming, it's x squared. The question is that from which bean, which two beans x's are coming, which two brackets the x's are coming. For here, the x is coming from 1 and 3. For here, the x is coming from 2 and 3. Here, x is coming from 1 and 2. Here, the x is coming from just 3. And y is coming from 1 and 2. Here, y is coming from 2. The bracket 2 actually. You see, that's why I marked it x2 and y2, x3 and y3, and x1 and y1. To demarcate from which bean it's coming from. Which bracket it's coming from. Y is coming from 2. Sorry. 1. Here y is coming from 3. Here x is coming from 1, y is coming from 2 and 3. Here x is coming from 2 and y is coming from 1 and 3. Here y is coming from 1, 2, 3. So did you understand now?
Yes, sir.
So therefore, x square y consists of all the x's from which bean it's coming, which brackets are coming. Right. So there are 3 brackets and it's x square y. So you're choosing 2 brackets. Jahan se x is coming. So it's 1, 3, 2, 3 or 1, 2. It's 3 choose 2. Therefore, this is 3 choose 2. So when x square, xy square, you're choosing the one position, say, which bracket say x is coming. It's 3 or 1 or 2. So therefore, its sum is 3 choose 1. This 3 is 3 choose 1. Y cube is 3 choose 3. 3 choose 0. 0 threes. And this is 3 choose 3. Did you understand this, guys? Swati, did and others did understand?
No, sir, I understand it.
You didn't understand?
Sir, I understood it.
Okay. All of you understood this, guys? So therefore, when there are n bins, the coefficient of x to the power k is nothing but out of this n bins, which k bins you are selecting, jahan se x aa raha hai, from which x is coming. And automatically the rest n minus k bins will be selected for y automatically. Okay. So therefore, iska coefficient will be n choose k because you're selecting k brackets, the beans of k, x and y out of this. So therefore, this summation is nothing but summation of n choose k, x to the power k, y to the power n minus k. Okay, great. So let's see some, if you can observe, if you put x and y to be 1, you get summation of n choose k, that is 2 to the power n. Exactly, that is what we got here. Okay. Here, if you put x is equal to 2, you will get this 2 to the power k, and y is equal to 1, x is equal to 2, y is equal to 1, you will get exactly this. So it's 3 to the power n. 2 and 1, 3 to the power n, summation right hand side. So binomial theorem was actually the underlying principle which connected the method 1 and method 2. Okay. Did you understand this, all of you? Great. So let's move on to multinomial theorem. It's a similar advanced idea of. So it was asked that instead of this x and y, what if there are m such quantities and you're powering it n? What if there are n such quantities and we are powering it m? So first is the question is therefore how it will, how every expression here, the individual expression has something it looks like, right? How is the individual expression will look like? So the m degree, so it will look like something like this. x1 से कुछ आएगा. Let's say you do x1 plus x2 plus x3 whole cube. So if you just add it up, multiply it up organically, x1 square plus x1 x2 plus dot dot. So you will see that this thing will be coming up. So you will see that it will be x1 whole to the power something k, x2 whole to the power something k1, x2 whole to the power something k2, and x3 whole to the power something k3. So the sum of these three is equal to n. This it will be coming up. This will be coming up. So therefore, the question of multinomial theorem is nothing but to ask that what is the coefficient of x1 whole to the power k1, x2 whole to the power k2, dot xm whole to the power km, such that k1 plus k2 for each such k1 k2 such that it's equal to n. This is our summation for each such pair, the tuples of k1 k2. For example, it can be x1 plus x2 dot xn x5 whole to the power 7. The elements can look like x1 squared, x2 1, x3 cubed, x4 1. This is one such element, and x5 whole to the power 0. Okay, it can be like this. So इसका coefficient क्या होगा? What will be the coefficient of this? This is the goal of multinomial theorem. It will approach the same. Okay, you understand the problem, all of you? All of you understood the problem? Yes, did you understand it? Everything that we have taught till now? All of you understood the problem, guys? What we are trying to address here? Great. So therefore, let's try to do this. So there are m beans, right? N beans and n m variables. M variables and n beans. Now we think about how it will happen. I will give you 1 minute to think. Yeah. You think about how it will happen. M variables and n bins. So what will be this? That means out of this, so this coefficient will be first select step 1 is select K1 bins for x1, then out of the remaining K2 bins for x2, then K3 bins for x3, dot. Finally, Km bins, Km minus 1 bins for xn minus 1. Once you select all this, automatically Km will be selected automatically. K1 for x1, K2 for x2. That means out of those n bins, you're selecting K1 positions for x1. N bins is selecting K1 positions for x1. Then out of the rest of the things, so first select K1 positions for x1. That is n such n is there, so n choose K1. Then out of the rest, you select K2 for x2. Once you select x1 ke liye, given you have selected for x1, you will select then for K2 for x2. This will be multiplied. So rest is n minus K1. Then you choose K2 for x2. Now next is, now you have chosen K1 and K2. So it's n minus K1 minus K2. Then you choose for K3 for x3. It will continue. Therefore, this will be nothing but first choose for x1. Then given you have chosen for x1, you will choose for x2 out of the rest. K2 places. Now given you have chosen for x1 and x2 out of the rest, this you will choose for K3, and this will continue till n minus K1 dot Km minus 1, choose Km. Now observe that this is nothing but, since summation of Km is equal to n, this is nothing but Km. So it's Km, choose Km, that is 1. So let's expand this. This is nothing but n factorial by K1 factorial times n minus K1 factorial. This is nothing but n minus K1 factorial times K2 factorial times n minus K1 minus K2 factorial times n minus K1 minus K2 factorial times K3 factorial by n minus K1 minus K2 minus K3 dot. This will continue till n minus K1 minus Km minus 1 factorial by Km factorial, and this minus this is 0 factorial. So observe that we are expanding n choose k. Observe that this and this will get cancelled. This and this will get cancelled. This and the next one and this will get cancelled. What is the final form? The final form will be therefore what is left? N factorial, K1 factorial, so it's left is n factorial by K1 factorial, K2 factorial dot Km factorial. This is the final form. 0 factorial is 1. So n factorial. So all of you understood this, guys? Did you understand?
So I partially understood it because I mean I don't understood from, I mean, how are we taking K1 bins from N1? There are N1 bins now.
Total n bins are there. Whole to the power n. It's x1 plus x2 plus xm. So every variable is it's taking a variable from each one of them and making one such variable. So how many such combinations or variables are there? The n bins here, n bins are there. Similarly, you're multiplying n times this one. Did you understand? Please tell me what's your doubt. I will explain it to you. The m bins, n bins, m variables in each bin. It's multiplying n times, so it's n bins. 1, 2, 3, dot n. So each variable is this. So it's saying that how many ways to choose 2 x2s from here, n bins, that is n choose 2 times the rest is n minus 2, that is 7 minus 2, that is 5. Rest of the 5 say we will choose 1 for x1, x2. That is 5 choose 1. This one is 5 choose 1, 7 choose 2. Rest of the say now you have 4, 4 choose 3, and now 1 choose 1, and 0 choose 0. This is exactly what is happening. Did you understand, Swati, or not? Tell me which doubt you have. Please tell me your doubt. I will clear it out.
So can you explain it from the part where we choose K1 ends?
No, we are not choosing K1 ends. We are choosing K1 xis.
Yeah, well, I mean K1 exercise, yeah, from that part.
So understand how will we make this variable? We need K1 xis, right? How many xis are there possible? How many beans are there? N beans.
Yes, sir.
So we are choosing K1 such bean. Which K1 bean से xi x1 आएगा? So we are choosing those K1 beans out of those n beans, right? Now we have selected those beans. From one bin only one variable can come. So from the rest of the n minus K1 beans, we will select K2 beans for the x2, right? Because from one bin only one variable can come. That is n minus K1 times by choose x2. Choose K2. Because x to the power is K2. And this continues till the last point. We are multiplying because first we select K1 beans for x1, then we select K2 beans for x2, then we select K3 beans for x3, and it continues.
Now I understood, sir.
Okay? Did you understand?
Yes, sir, now it's clear.
All of you understood? SK, did you understand?
Yes, sir. I just wanted to ask, like, we are converting the whole problem to bins because we can think in terms of choosing, because multiplication of that power is difficult thing. That's why we are doing it for bins, because that's the thing we can easier to work on.
Actually, it's like it's a very natural thing. Like, I mean, we understood, we are not converting. It's actually what's happening. Here we are converting into something else we know, but it's actually here that's exactly what is happening. We're not converting into something. It's coming here. You can see it's coming here that it's coming here that the x's are choosing some bins. So I'm not choosing, the variables are choosing actually.
Hmm.
So you have to understand in depth, okay? When we are trying to, yeah. Okay, all of you clear with this, guys? Yes or no? Yeah, Anubhav. Anubhav or Anupam? Who asked?
No, sir, I raised it by mistake.
Okay. Everyone clear? Any doubts, guys? I will explain it to you properly if you have doubts. Okay. So this is what is multinomial theorem. Oops. Anyways, but I will not end, but I will do one more problem. The idea that was left here. We have done multinomial wall and stick method. So what is the wall and stick method? What's an actual question it's coming from? Everything comes from a story. So if you have seen here that for binomial, for multinomial, what we did that x1 plus x2 plus dot xm whole to the power n is coming out to be summation is equal to n, right? And n factorial, k1 factorial, k2 factorial, dot. So it will be k1, km factorial, x1 whole to the power k1, x2 whole to the power k2, dot, xm whole to the power km. This was the summation. The natural question is that this xi, ki is going to be 0. So you can see for binomial, you can see they are exactly for k is equal to 0 to n plus 1 such variables, x to the power n, x to the power n minus 1, y. The question is for multinomial, how many such variables will be there? How many such variables will be there for multinomial? That means how many summations can you will sum it up? How many summations can you will sum it up? For each variable, you will sum it up, right? Summing up for each variable, each ki tuple. How many such tuples are there? So the question is that how many such tuples k1 dot km are there such that k1 plus dot km are integers and it's equal to n, ki greater than or equal to 0 and ki are integers. We are counting the number of such tuples k1 dot km, so the sum is equal to n and ki is greater than or equal to 0. How many such tuples are there? This is called a ball and stick method. How do you do that? So it's also same as how many ways you can distribute in things in to m peoples. So there are m boxes. These boxes are how many such ki's for xi's. So you have n degree. So you want to distribute into m places. It can be 0 too. So it's asking how many ways you can distribute n objects into m places. It's equivalent to this also. So how do you solve this? This is called ball and stick method. It's a bit intricate. Try to understand it very carefully. So let's take an example. You have K1 plus K2 plus K3. We took M equal to 3 and N equal to 5. N equal to 7, let's say. The N objects, N similar objects, okay? 7 similar objects. These are the balls. 7 balls are there. N equal to 7. The degree. The 7 balls are there and K places are there. The K places are there. So how to share this into 3 places? So it's like how to partition it into 3, you know, how to divide it into 3 such places. So the partition, what they did is that since there are m boxes, they added m plus 1 partitioning elements. Like partition elements are this big wide ball, big wide sticks. That's why it's called ball and stick method. So m equal to 3, they added 2 sticks. So first in the recipe they put in 7 balls. And in the next part they put in m minus 1, that is n balls. In the next part they put in m minus 1, that is 2 sticks to partition, to demarcate the boundary of partition of this. These are these 2 sticks. So now observe that let's take an arrangement of this. This is one such arrangement. Let's take another arrangement of these 7 balls. I think, yeah, of the 7 balls and 2 sticks. Let's take another arrangement. Let's take another arrangement. So observe that each arrangement corresponds to a solution. For here, it's nothing but 2 for K1, 3 for K2, and 2 for Km. Here, it's 1 for K1, 1, 2, 3, 4, 5 for K2, and 1 for K3. Here, it's 0 for K1, 7 for K2, and 0 for K3. There is nothing on the right hand side. So therefore, the number of such set, if you call the set n, the number of elements of the set is equivalent to the number of ways of arranging seven, that is n balls plus 2, that is m minus 1 sticks. But these are all distinct. These are same, okay? I mean, this ball are not distinct. So essentially, there's the arrangement type of thing. So it can be transferred into combination problem, where since these the ball are not distinct, there's an arrangement. This is same as if understand this very carefully. This is same as if there are 9 places that is 7 plus 2, that is n plus m minus 1. This balls and this is the sticks, the partition के लिए. And you have n balls and 2 sticks. So using this objects, you have to arrange it here. Essentially, it's nothing but out of this n plus m minus 1 places, there is 9 places. You have to choose 2 places for this 2 sticks. This choosing is equivalent to this arrangement. If you choose in a different way, you choose another thing like this. This is equivalent to this arrangement. So therefore, this number of values, number of elements of n is nothing but number of ways of choosing m minus 1 places for the sticks, right? M minus 1 places for the sticks, for the boundary sticks, out of n plus n balls and m minus 1 sticks to get places. That is, number of ways of choosing is what? It's m plus n minus 1, choose m minus 1. So that is the value. All of you understood this, guys? Yes, no, maybe. If not, please raise your hand. Very good. What about others? Sure. From which part can you say, Sinjini? From which part you want me to explain?
So the next slide.
Okay.
So this slide.
Okay. So we are trying to arrange 7 balls and 2 sticks because each arrangement corresponds to one solution. So here we can use the permutation formula. Why? Because permutation formula demands the existence of the distinct nature of the balls. But here the balls are not distinct. So we need to deal in a different manner. So observe that each arrangement is nothing but we have 7 balls, that is n balls, and 2 sticks for the partitions, and m minus 1 sticks for the partitions. So each arrangement is nothing but out of this n plus m minus 1 places, is 9 places, selecting 2 places for the sticks. So once we select 2 places for the sticks is equivalent to one arrangement of such. As I showed, if I would have placed a stick here, there is a different arrangement of these balls and sticks. The solution is 5, 1, and 3. Here the solution is 0, 0, and 7. So therefore, it boils down to choosing m-1 places for the sticks, m-1 sticks, 2 places for the 2 sticks out of the n places, n plus n-1 places. Did you understand now, Srinjini?
Yeah.
That is nothing but n choose m plus 1, choose m-1. Yeah, Sucheta?
So, you said that the balls were not distinct. What if the
Yeah.
balls were distinct? तो difference क्या था?
If the balls are distinct, understand that if the balls are distinct, like 1, 2, 3 or balls are there, then here 1, 2, and 3, and here 1, 2, and 3 are different. You understand? Because it's like, it's like saying that I'm sharing all Dairy Milk's 50 rupees silk chocolates to you, versus sharing that I will share 5 kit, let's say there are 10 balls, 10 chocolates, Dairy Milk silk. Instead of that, I'm telling you that I will share 5 Kit Kats, 2 Dairy Milk silk, and 3 Bonville chocolates. So the arrangement will be different, right? Because if you get one, if Sucheta gets 3 chocolates, in one case she may get 1 Bonville, 1 Kit Kat, 1 Dairy Milk silk. In another case, she can get all 3 Dairy Milk silk. In another case, she can get all 3 Bonville. So all these things are different, but we are not considering that. We are considering all same chocolates. Do you understand, Sucheta?
Yes, sir.
Sure.
अब सर जो आप कहना चाह रहे हो वो तो समझ गई कि डिस्टिंक्ट यहाँ पे, बट यहाँ पे हमने ये बोला कि फिर डिस्टिंक्ट नहीं है. Then.
Yeah, here it's not distinct. I mean, what's your question exactly? Can you explain once again?
You said that the balls are not distinct. I understood what you mean by that, but यहाँ पे हमने particularly ये बोला क्योंकि that the balls are not distinct.
Here the balls are not distinct. Here the balls are not distinct because we are arranging the n degrees, the m balls among those m places. So the balls are not distinct here. The arrangement of this, like we're counting it, so it's not distinct.
So I'm not able to get the reason.
Okay, just 1 minute, okay? So your question is that why it's not distinct here?
Yes, sir.
Okay. So this problem is this. The problem is this, that you have k m places and you're distributing the value n. Okay, like k1 will take value 1. Okay, so one solution of this is what? Let's say one solution of this is what? 2, 3, 2, right? If it were distinct with this solution only, it will be different. For example, if k1 is equal to 2, if there were 2 different cases, different objects were there, it will be D1 and D2. But in this case, it's just D1, like Dairy Milk, 2 Dairy Milks. If they are distinct, it will be D1, D2. Another case will be D2, D3. All the cases must be considered. But here the problem is only that the values of this, not the like the problem is defined like that, like non-distinct values. Did you understand? I don't know whether I'm able to make you understand or not. Right.
So not completely, but thoda bahut, I guess.
No, no, it's okay. I will make you understand. Don't worry. So, okay. So tell me, why do you think it's distinct? Which part makes you think that it can be distinct?
So it's the same as which part makes you think that it shouldn't be distinct. I don't know. It's just a question that came up in my mind that why particularly here it should be distinct. Like,
Okay, I will
if
give you an example. So, did you understand the question? The question is the number of solutions to this equation. Did you understand that portion?
yes, sir.
Okay, let's take a simple example. Let's take the set of all x and y, such that x plus y is equal to 5 and x and y greater than or equal to 0. Any other doubts? Yeah, I will come to you, Anubhav, okay? You want to say something regarding this?
Yes, sir.
I mean, you want to say something to me or to Cheenta?
I mean, I mean, I think I found an example which might help Shucheta understand.
Oh, sure, sure. Please go ahead. Yeah, tell me.
Yeah, so say there are 8 balls, right? And we mark those balls 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, say a given arrangement. Say there are 3 kids who I have to give these 8 balls to. Say the first kid I give 2 balls, the second kid I give 3 balls, and the other kid I give how many balls are left? 3 balls, right?
Yeah.
The first kid receives 2 balls. But if all the balls are identical, then it doesn't matter which 2 balls the first kid received, right? But if all the balls are not identical, then this first kid may have received balls 1, 2, or 2, 3, or 3, 4. All of these are different arrangements. So if the balls are identical, then it doesn't matter which balls. I mean, the balls themselves have nothing special about them. It's just the number of balls each person is receiving. But if the balls have some special property to them, like the numbering, then each arrangement. I mean, it doesn't matter how many number of balls they're getting. The which balls they're getting also becomes relevant. So that has to be put into calculation.
So, if you consider the same thing here, observe that if you count the same thing, observe we are counting the same thing twice. You understand? If they are distinct, if they are the same, and we consider follow the pattern of the distinct. Did you understand his example, Sucheta?
Yes, sir.
Sure, 100%, or you're sure?
So my question is, I understood what Anubhav was trying to say. I
Mhm.
understood that. But my question is, in this problem, why are we saying the reason behind we say that they are not distinct? I am not able to understand the why.
I mean, did you understand? We are trying to seek the solution of this equation.
Yeah.
So it's like there is a place of x and there is a place of y, and it's seeking a solution of 5. So I think she's trying to understand, like she's not getting why this problem transferred to this distinct problem and same problem.
Yes. Actually, my question is this only that why does this happen? Like, why they are not distinct?
Okay, just let me think. I mean, yeah, SK, you want to say something?
Am I audible?
Yeah, yeah.
Yeah, I wanted to tell this situation, Shweta. So we can see 5 as 1 plus 4 or 2 plus 2 or uh, what? No, yeah, 2 plus 3, 3 plus 2 or 4 plus 1, that thing, right? Now we can now just replace 1 and 2 by uh, 1 dot and 2 by 2 dots. Like put 1 in one container and 2 in two containers. 2 in another container. 1 in one container and 4 in another container. So it will be one ball in one container, and the other container will have all 4 balls. So that's how the sum it is like that. So the number 1 plus 4, that one is one ball, and that 4 is nothing but the 4 balls. And we need the sum. That's why all the balls are identical. If they are not identical and they're distinct, I think the problem will convert to just find the number of words that can be formed from these letters, or that kind of thing. We are trying to find the constraint is the sum, that sum of the balls in those containers should be this, and we are trying to substitute that sum by the number of identical balls. That's what I think.
Did you understand, Rizana?
Yes, sir.
100% fully?
Yes, sir. Yeah.
Okay, great. Thank you, SK and Anubhav. Okay. So any other doubts from this whole thing? Because we have completed entirely what I've planned to do. So we have done some problem based on this arrangements and all these things and permutation combination and then binomial theorem. We understood that idea of, conditioning, adding law of total probability kind of thing, which we will learn, law of total combinatorics. Then we did binomial theorem, multinomial theorem, and then we did the ball and stick method. So any doubts? All of you understood? Say an yes if you understood everything till now. Great. Great. Swati and Jyotish, did you understand? And Moitro? I don't know Moitro is here or not. Yeah. Moitro, Swati and Jyotish, did you understand? Kaushik, did you understand? Great. Jyotish may not be here. Yeah, he is not here. Moitro, did you understand? I don't know if he's here or not. Anyway.
Yes, sir. Yes, sir. Yes. Perfect. Clear.
So now we have done entirely till this point. Okay. So next day, like Thursday, we will be doing problems till this point. They will be doing past year problems. Okay, and the past year problems will be given as homework, and some more few problems will be given. You should read this entire till this section 1.5. You should understand. And from next week, the theory class on Monday, we will be starting this axiomatic probability. Okay, we'll do the entire axiomatic probability, and then we will do the conditional probability part also. Okay, you should follow this book. This book is the best of the lot, and you can try out these problems out here. Okay, a few of the problems will be given from here also. And what else? And then next week we will be starting axiomatic probability. We'll do the basic probabilistic inequalities, like Boole's inequality and all those inequalities. Then we'll do the past year problems, and then we'll do the conditional probability of basic understanding. Then third week we will be starting the conditional probability and Bayes theorem, and we'll do the Bayes theorem. And this will complete the entire probability syllabus. Just probability topic syllabus that is in the syllabus of IIT JAM and ISI, and then we will move on to random variables on the fourth week. This is the plan as of now. Okay. So any questions from your end, guys? Any suggestions? I hope the pace is fine, everything.
Sir, I noticed that this Blitzstein also has a lecture series on YouTube. So should
Yeah,
we
you can
also
also
use
follow
that?
that. Yeah, it's beautiful. So you can also follow his lectures. And in fact, I had a talk with Blitzstein over LinkedIn. He told me he will come on live with us, but he is a busy person. I am trying to make him come to live in Cheenta. Let's see. But yeah, so that's the basic idea. So you can follow his lectures, read his book. So if you can read his entire book, you should be a master of probability. I mean, the basic probability, you should be a master of it. So that's why it's very important, guys. So you should be doing that, okay? So you should follow that lecture and on your own pace, at your own pace. So you have 6 months to focus on probability and make the best time of yours. That's it, okay? Any other questions, guys? Follow the exercise behind this book. If you have time, solve them extra. Otherwise, we give homework of past year papers. I've already segregated that. So yeah. Any other questions, guys? Okay. Okay. Thank you guys. Good night. I will see you. Like the other faculty will never go. Will see you on Thursday with past year problem solving. Yeah. Bye bye. More problem solving.
So in this problem, what we have to solve this thing. Here you say that draw one observation in at random from the set 1 to 100, and what is the probability that the digit of n square is 1. So actually this is a classical probability problem, and here you only have to find the total number of events and favorable number of events. So here we have to find the probability that the last digit of n squared is 1. So n actually follows discrete uniform distribution. I think most of you don't know this distribution, or you can probably seen this distribution after 2 or 3 class. But so actually n follows discrete uniform 1 to 100, but we don't have to use this thing or use this criteria. We will solve this in general combinatorics way. That is actually, if n is 1 and 9, then if we square, then it will be give 1 and it will be give 81. So the last digit will be 1. So if you clearly observe, like 1 to 9, 11 to 19, um wait, 21 to 29, up to 91 to 99, because if I do square of 100, it cannot be give last digit 1. So if you clearly observe, then you can see the last digit will be 1 if you take the two number 1 9 at the last digit of this series. That means here 1 to 9, two digit 1 and 9. Here also 11, 19, 21, 29, and the middle of the numbers. If you square of any of the middle of the numbers, you cannot get the last digit of n square is 1. You have to observe this thing. So I will suggest for combinatorics, do not follow any formula or anything, any high formula that is you can that can confuse you. Okay, so in basic way you can solve this thing. So just observe this thing here. Now you have to count the number of digit of n square is 1, whose last digit of n square is 1. So see here, 11 to 19, 2, 21 to 29, there is 2 digit. Up to 91 to 99, there is also 2 digit of such criteria, that is the last digit of n square is 1. So now observe, the series is from 11, the first digit of this series. The first digit of this series is 11. The first digit of this series is 21. Now the first digit of this series is 91. So see, there is the number of group is 1, 2 up to 9. So there is 9 group. Okay. And this is the last group where also we get the 2. So actually total number favorable number of cases equal to 2 plus 9 into 2, so 20. Now our required probability equal to See, we will draw one observation in from the set 1 to 100. So it will be it we take one from 100, so it will be 100 C1. So it is 100. Now in the numerator it will be 20. So answer will be 1 by 5. Okay. Now I move to the next question. Very interesting question of ISI, that is said that there is a flag which is to be designed with 5 vertical strips using some or all of the 4 colors, that is green, maroon, red, and yellow. In how many ways we can this be done so that no two adjacent strips has the same color? So the main criteria is this, that is no two adjacent strips have the same color. So this type of problem, to solve this type of problem, don't be confused in the examination hall. You have to just draw the thing. Suppose you think that is a flag. So, and there is 5 vertical strips, like one, it is one, two, three, four, sorry, um, it's five strips. Now see, here we can use some or all of the 4 colors: green, maroon, red, and yellow. So, and the criteria is the adjacent strip have the no two adjacent strips have the same color. So that is like, if it is green, then this strip cannot be green. Okay. So I take a general case to make you understand clearly. Like it is a case one, that is it is green, then then the next strip cannot be green. It will be any of maroon, red, and yellow. So let us think it will be red. So that thing. Now the next strip will not be red. Okay, because no two adjacent strips have the same color. It can be green also, but it cannot be red. It cannot be red. So see, it will be green. Then next also that not be green. Now it can be maroon. Then the next strip cannot be maroon. It will be any of the three. Like it will be like red, again red. So this type of thing. So if you think clearly this thing, if you observe the thing clearly, then you just have to choose one color. For the first strip, you just have to choose one color from green, maroon, red, and yellow. So it will be 4C1. Now you all know about the multiplication formula, multiplication rule of combinatorics. That is very important. So I said that you don't have to memorize any important critical formula, but there is two basic rules of commentaries, that is additive rule and multiplicative rule. It is everywhere. It is actually, it is the actually the main criteria of the total commentaries. All sums of the commentaries is of the base of these two things. Okay, so here you have to multiply. Why? Because see, total things are done in simultaneous way. That is, you have to choose the color of the various strips, or of the 5 strips simultaneously. So you have to choose one color from the 4 color. That is 4C1. Next, see, you cannot use. Now let us think that is green color. In your memory, you just think it is green color. Then think I cannot use green. So we have just 3 extra color, that is maroon, red, and yellow. So we can choose one color from the 3 color in 3C1. Then think you choose any 3 color except the green. So think it is red. Then you can take you can choose next one color from the remaining 3, you can use the green, but you cannot use the red because you use red here. So again, this will be 3C1. I think it is understandable to you. Then again, we cannot use the color which I use the previous one. So we use like the green color. So we cannot use green. So we use maroon, red, or yellow. So from 3 again choose 3C1. So in this way we will solve. So the answer will be, I think the answer will be number. Okay, total number of ways is 4C1, 3C1. Oh, 4C1, 3C1, 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 1, 2, 3, 4. Yes. So 4 into 3 to the power 4. So 4 into 9, 27, 81. Yeah. So so I think it is understandable. That is, you have to choose one color from 4, that is in 4C1 ways. Again, so you choose one color from 4 colors in 4C1. Then you cannot use that color, that same color. So you can choose one color from 3 for the second strip. For the third strip, you cannot use the color of the second. So 3C1. So so on. Okay. That's the main thing. So by multiplication theorem, multiplication theorem or multiplication rule of combinatorics. Hmm, okay, next. Okay, so it is actually a problem where if you have some distribution idea, then you can understand this thing more clearly. But mm I will I want to share the solution as in combinatorics way, that is you can understand easily. So see, first you have to read the problem properly. You have to read any combinatorics problem very properly and very organized way, and every line you have to read, because it is like the problem of, I mean, it's like a problem of problem solving of quiz, or you can see here your intelligence is checked actually. Okay, how you can read the problem properly and analyze the problem, that is the whole thing. Okay, okay. So anyway, the question is, a shopkeeper has 12 bulbs of which 3 are defective. Now she sells the bulbs by selecting them at random, one at a time. That is the main thing. That is, she sells the bulbs by selecting them at random, one at a time. That means it is actually a simple random sample without replacement. But you will study in sample survey this thing. But I will say you this thing in combinatorics way. But I just tell you this thing. If you are interested, then you can read this thing. If in any statistic book you can find, it is actually simple random sampling without replacement. Without replacement. Okay. Hmm. So then we have to find the probability that seventh bulb sold is the last effective one. So now we have 12 bulbs. We have 12 bulbs. Okay. Now here three are defective. Three defective. So remaining nine will be good bulb. Okay. Now first actually we draw six bulbs. That is not drawing. That is sale. That is the shopkeeper actually sells the six bulbs from the 12 bulbs at random one at a time. Think this way. That is, it is first bulb, it is second bulb, third bulb, fourth bulb, 12 bulb, and shopkeeper, this is shopkeeper. Okay, now she sells the bulbs one. Now one bulb left. Then she have 11 bulbs. Okay, now second bulb sell. Then she have 10 bulbs. In this way. Okay, so actually this is simple random sampling without replacement. That is, when she sells the bulb, she cannot take the bulbs from the the customer. Then not. So it is actually simple random sampling without replacement. Okay. So here we have to find the probability seven bulbs sold is the last defective. That means last defective means there are three defectives. So two defectives are included in the first six bulbs. That is, we draw six bulbs, and here two are defective and four are good. Two are defective and four are good. Then it is the last trial. That means it is the seven bulbs sold. So at the seven bulbs sold, that is the case. It is the main case. So how to find this thing? See, okay, I am sort of page. There is a sort of page. Wait. Okay. See. Okay. So first you have to find the denominator. That means the total number of cases. Okay. See. So total number of case equal to, that is like the thing you choose 7 bulb from 12 bulbs because it is without replacement case. Here we cannot include the permutation or arrangement, like you choose first from 12 bulbs 1 bulbs, that is 12C1. Then you choose from 11 1 bulb, 11C1, 10C1, up to um number of bulbs sold 7. So up to 7C1. 7C1 or wait, 12 factorial, 7 factorial, 8C1 I think, because there are 7 bulbs we drawn. Okay, so we want to draw 7 bulbs. So 12 7 5 6 wait 1 second, 12 7 5 6 yeah, no, 6C1 it will be. Like you all know na, the permutation cases, that is 12C1, 11C1, 10C1, up to 6C1. Okay, this thing. But in this multiply, in this multiply there is including of the permutation or arrangement. So we have to divide this by 6 factorial. We all know this thing. I want to say this once more, because I think you don't understand. See, there are 1 to up to 12 bulbs. So first you choose from 12 one bulb. This is 12C1, then 11C1, then 10C1. When you completed the 7 bulbs sold, then you will stop. Like it will be 6C1. So the number of bulbs sold, 12 minus 6 plus 1 equal to 7. Okay. But here it is actually the rule of multiplication. But here this is inclusion of permutation. But here we cannot include the permutation because we are short of the bulb. Na? The bulb one is gone, then second bulb is gone. So there will not included of the permutation. So we will divide this by 6 factorial. So it will be
Excuse
12.
me, sir.
Hello?
Hello. So, could you please explain this again?
Yes, I will explain this thing. 1 second. Wait. So this is actually the total number of case 12C7. How we can get this thing? See, we have 1, 2, 3 up to 12 bulbs, and we choose here C. What is the probability that a 7 bulbs sold is the last defective one? So to find this, we have to find total number of events. Total number of events means how we can choose 7 bulbs from 12 bulbs. Actually, it is like combination. It is formula that is 12C7. But I want to say you how it is come. How the formula is come. So see, there are 12 bulbs. So first you choose, that means shopkeeper choose from 12 bulbs 1 bulb, 12C1. Then she choose from remaining 11 bulbs 11C1 up to 7 bulbs sold, that is 7C1. Okay. Now see that it is actually I do multiplication. So when we use the multiplication rule of combinatorics, then there is inclusion of permutation. But 12C7 means there is combination. There is no trace of the permutation. That is arrangement. So we cannot arrange the 7 bulbs. We cannot want to arrange the 7 bulbs. Okay, because we choose 7 bulbs from 12 bulbs. It is actually we sell one by one the 7 bulbs. Okay, so see, this is 12 factorial by 7 factorial. So 12, 11, up to, I mean 7, 8. Yeah, and 7 factorial, 5 factorial. So this is the main thing. Okay. So here 12, 11 up to 7. So 7 bulbs we have to choose. So 12 minus 7 plus 1 equal to 6. Okay, so we have to choose one more, 8C1. I think it is understandable. 12C1, 11C1, up to it is sort of bulb, na? So 7C1 and 6C1. I also confused this thing. Okay, sorry. So 12C1 and 11C1 up to 7C1, and there is other bulb 6C1. So remaining from 6 bulb we choose one, so 6C1. So in this way we can get 12C7, because there is what I want to say, that is there is no trace of permutation. That there is only combination. That is we choose 7 bulbs from 12 bulbs in 12C7 ways. Now we have to find the favorable cases, that is the 7 bulbs sold is the last defective one. Okay, so that means we choose 6 bulbs, and first 6 bulbs, and then the 17 bulb. So when we choose 6 bulb, that means um, the probability will be like this, that is 12C7, and the upper, that will be um there is 12 bulbs and okay, so from 12 bulbs, where is it? 9 good bulbs and 3 defective bulbs. So from 9 good bulbs we will take 4 good bulbs, so 9C4, and from 3 defective bulbs we took 2 defective bulbs, so it will be 3C2. And that is actually 6 bulbs chosen. Let's see, this is 4, this is 2, so 6 bulbs are chosen. But in the last case there is actually, wait, i have to uh, I have to rewrite this thing. Okay, so this is actually 6 for 6 bulbs. Okay, in the last case there are remaining, how much bulbs are remaining? See, 12 bulbs is there, 6 bulbs gone, so there is will be 6 bulbs, and defective bulbs will be remaining 1, because here we choose 2 defective bulbs and remaining is 1. So it will be 1 by 6. Oh, that is actually I do mistake. It will be 12C6. Okay, uh I will tell this thing one more way. Okay, that you can understand more clearly, because I think it is you are don't understand easily, I think. Okay, that is the page. Oh, okay. I am rewrite the solution. See, first, see, there are 1, 2, 3 up to 12 bulbs. Now we have to choose 7 bulbs from there. That is 12C7. It is total number of ways. Okay. Now see, we have to find favorable number of events. Favorable number of events. That will be like this thing. First we choose 6 bulb, and then we do the 7th trial. Okay. Now this 6th trial we get 2 defective and 4 good. Why? Now here is said that we have to find the probability that the 7th bulb sold is the last defective. So here in the 6th trial, 2 will be defective bulbs. Okay. So it will be like, from 9 good bulbs we choose 4 good bulbs, that is 9C4. Now from 3 defective bulbs we choose 2 defective bulbs. Okay. Then the last case, that is the main case, that is the last defective case, that is 7th trial. What we will do in the 7th trial? Now in 7th trial we will choose just 1 bulb from 7. Okay, so it will be, the defective bulbs is 1 and we choose the 1 bulb, so it is 1C1. Now the probability will be 9C4, 3C2, and it is 1C1, and here it will be 12C6, and it will be 6C1. Okay, yeah, 6. So I think it is understandable. One more I will I am saying. Say, see, the first 6 trial we choose 6 bulb, that is 12C6, and the upper part is 9C4 into 3C2, because there is from 12 bulbs 9 is good and 3 are defective. So from 9 we choose 4 good bulbs, it is 9C4, and from 3 defective bulbs we choose 2 defective, 3C2. Now in the last trial, that is 7th trial we left 6 bulbs. So from 6 bulb we choose 1, and defective bulbs is 1, that is 1C1. Now you have to calculate this thing. It will be 9 factorial, 4 factorial, 5 factorial, 12 factorial, 6 factorial, 6 factorial, 6. So it will be 9 factorial, 6 factorial, 6 factorial, 12 factorial, 4 factorial, 5 factorial, 1 by 6. So 12, 11, 10, 6, 5, 6, 5, 4 factorial, 6, 1 by 6, 6, 6, 5, 2, 2, 3, 3, 4. But I do mistake. Again, I can do mistake. See, wait. Can you please calculate and say me the answer? I think 6 factorial, 6 factorial. Yeah, 6 and 6. Yeah, by 12 factorial, 5 factorial, 4 factorial, 1 by 6. So 12, 11, 10, 9 factorial, 6 into 5 factorial, 6, 5, 4 factorial, and 1 by 6. 6, 2. 2. It is 1 by 44. But I think I do have anywhere the mistake.
So you missed 3C2 in the numerator.
Oh, thanks. Yeah, I do many calculation problem. So okay. Thanks. 3 by 44. Okay. I actually do mistakes the total number of cases. I take 12C7 again and again. But see, this is actually you have to split. Nah, this is 6, the first 6 bulbs and the last 7th trial. Okay. So this is the split thing, and it is you do multiplication by multiplication theorem. It is actually not easy problem. Multiplication. Because this is the hypergeometric model. I can write this thing. Okay, multiplication theorem. What we have to see, this thing actually this thing is hypergeometric model. You can study this thing if you want, if you're interested. Hypergeometric model. And this is actually the what is the problem is thing that is the C sells the bulbs by selecting them random at 1. This is actually if you understand clearly, this is the sampling scheme, which is SRS WOR, simple random sampling without replacement. I think it is understandable to you. I think I am able to give you this thing understandable. Okay. So the next problem. It is important problem actually, very important problem for make
Excuse
your
me, sir.
yeah, say.
So sorry to interrupt, but sir, can we do this question by different way?
Yeah, say, please say.
Sir, let us. I mean, if the six bulbs are sold, then the remaining six are there, right?
Yeah.
I mean, can we choose in such a way that we will choose a bulb from the six bulbs? That is the total number of cases, and the favorable cases could be like we have uh, we have remaining six bulbs, and in that one bulb is defective, and the other five, the remaining five are non-defective. So can we do it like 5C4 into, no, sorry, 5C2 into 1C1, and then by arranging it, we can calculate the probability that the first bulb will be defective.
Acha. Say you have you say once again. I write the thing. Say
So
once
like
again.
6 bulbs are already sold and there
Mm,
are remaining 6.
mm.
So choosing one from them, the total number of cases will be 6C1,
Okay.
and the favorable cases could be 5C. I mean, there are five in the remaining 6 bulbs. Five are defective and one is not defective.
No. See, here are only three defective bulbs na in the question. See, in
But
12
sir,
bulbs,
uh-huh.
yes. Okay.
But sir, two defectives are already sold now.
Yes.
So can't we
So
just
there is only remaining of one defective na.
hmm.
So we have to choose this one from one. That is not choosing actually. There is only one case, not five.
But yes, sir, there is one case for defective, but for non-defective, there are left five
Oh,
cases.
oh, okay, okay. So you want to say there is you have to take one C1 into five C1. No, what you
Into
say?
1C1 upon 6C1. I mean, all I want to say is ki if we don't focus on the bulbs that are sold and focus on the bulbs that are unsold, so can't we solve
Oh,
this question
acha
by
acha acha.
permutation?
Okay, okay. Complementary cases. Okay.
Yes.
Yes, you can obviously say, obviously do this thing. You can do this thing by taking complementary cases. Yeah, yeah, absolutely right. It is another case. It is another way of solving. Yeah, you can also do this thing. It is actually complementary cases. What you want to say, right?
Okay, so can we solve it by that method? So, I mean, I will not get confused.
Okay, so in the complementary cases, if I do this thing, what is the probability that seven bulbs sold is the last effective? So if I take complementary case, then it will be one minus um, probability complement. It is one minus this thing. So probability that seven bulb sold, that is last effective. Okay. I think that will be difficult because probability that I say one second probability last seven bulbs sold is seventh bulb sold will be last effective. If you take complement na, then it will be difficult, I think, because the complement of this event will be seventh bulb sold will not be last defective. Okay, seventh bulb sold, that is six bulb already gone. It is the seventh case. Seventh bulb will not be last defective. That means that cannot do any meaning now. So it may be possible all defective are in the six cases. Okay, or it may be there is only one defective. So it will be a misery now. It will give you a problem now. So I think what I do in this method, it is actually the process. Because if you do complementary, then yeah, you can do by complementary method, but not for this problem because this is counting problem. So you can face problem. See, if I take complement, seven bulb sold will be not the last defective. So that means ki after seven bulb chosen, after the seven bulb chosen, there also maybe not maybe there must be some another defective bulbs. So that cannot make some meaning now. You will face problem to solve this thing in this way. Okay.
Okay, sir.
Yeah. So always you have to see which is which is easiest way in the combinatorics. Otherwise, you cannot solve in the examination hall or anywhere. This is actually the process. Okay. So next question I have to I think I cannot get total time to solve all the 20 questions. I will give you to solve as exercise, but I will do the important problems. Okay. So is this is one question that is good question. Yeah, matrix question. You all do linear algebra. There is not linear algebra concept needed. A matrix concept will be needed. So think S is the set of all 3 cross 3 matrices A such that the among 9 entries of A there are exactly 3 zeros, exactly 3 ones and exactly 3 twos. The number of matrices in S that have the trace divisible by 3. You all know trace. Trace is actually sum of the diagonal elements of a matrix. Principal diagonal element of trace equal to sum of principal diagonal elements of a matrix A. Okay, let us think by the matrix. Okay, so you have to find that such matrix where the trace is divisible by 3. So first thing in the terms of the principal diagonal. See, we have in our hand there is 3 0, there is 3 1, there is 3 2. If the diagonal element, if the principal diagonal is diagonal elements are all 0, then it is divisible by 3 and it is the case 1. The case 2 is you have to think in this way. See how I am solving the question. Okay, it is the main thing because you have to click the question in this way because you have to say that trace is divisible by 3. So you have to first see how we can find trace and how it is divisible by 3. So to find trace, you have to see or you have to observe on or you have to focus on the principal diagonal. See, so if it is all 3 0, then it can be divisible by 3. Now the second trivial, that is actually the trivial case. The all 0, the all 1, the all 3, all 2, it is actually the trivial cases. So um, the next matrix is, it is A1, A2 is not A1. In matrix, suffix cannot be used, may not be used, A, B. Okay. So if it is 1, 1, 1, then it is also divisible. Then if it is 2, 2, 2, then also it is divisible. And the fourth case is if it is 0, 1, 2. Now that is once a case. And fifth case, if you think, it is actually 0, 1, 2 means 2 plus 1, 3 and it is divisible by 3. This is 2 plus 2 plus 2 equal to 6. It is also divisible by 3. Now what is the possibility? 0, 2, 1. That is not divisible. 2 is not divisible by 3. Then 2, then another case is like 2, 2, 4. It is also not divisible. So I take 1, 1, 2, 2. That's complete. Then I think no more cases available because I take all 0, all 1, all 2. Everyone is one time each, 0, 1, 2. Every element is one time each, every diagonal element 0, 1, 2. And then 2, 1, it is not divisible by 3. Also then 2, 2, it is also not divisible by 3. So that's the 4 cases A, B, C, uh, D. Okay, then it is super easy to you to solve this thing because see, it is like the dictionary problem. You all I think know the dictionary problem. You all do the thing here also. This thing, this is like that thing. Okay, so see, if it is 0, 0, 0, Then I have key. I have 1, 1, 1 and 2, 2, 2 left. Okay, then we have 1, 2, 3, 1, 2, 3, 6 places. And you have to fill by this thing. Also here 6 places, and we have 0, 0, 0, 2, 2, 2. Okay. Here also 1, 1, 1, 0, 0, 0. Here also here 2, 0, 2, 1, 2, 2. Now you have to calculate. So how many A where the diagonal element is 0 you will get? It is 6 factorial by 3 factorial, 3 factorial. You all know dictionary problem now. That is there is no permutation is 1 and 1, 1, 1. There is also no permutation is 2, 2, 2. So we have to eliminate the permutation. How we can eliminate the permutation? By divide this thing 6 factorial by 3 factorial, 3 factorial. Here also 6 factorial by 4, 0, 0, 0, 3 factorial, 2, 2, 2, 3 factorial. Here also 6 factorial by 3 factorial, 3 factorial. And for this 6 factorial, 2 factorial, 2 factorial, 2 factorial. Okay, super easy thing. You have to just draw the question. So it will be 654 3 factorial 20. 654 3 factorial. Okay, 6 5 4 20. Yeah, 20 20. It will be like 654 3 2 factorial 654 654, yeah, sorry, 6543. Oh, I can write this thing. Okay, 654, I think eliminate. 6543 2 will be eliminated, so it will be 6533 90 calculation. So total number of ways equal to 90 20 110 130 150. Okay, 20 into 3 plus 90 equal to 60 plus 90 150. Okay, it will be the answer. One thing in the comment box, which is we can also permutate 0 1 2 in 3 factorial different ways. So multiply the last case by 3 factorial. 0 1 2. Oh,
So it will also become 102,
yeah.
201.
Oh, okay, okay, okay. So you say yeah, 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 yeah. 0 1 2 2 1. Yeah, yeah. Thank you, thank you, thank you. Okay. Yeah, yeah, you are right. Absolutely right. Here we have to multiply 3 factorial because this 0 1 2 will can be permuted in 3 factorial also. 0 1 2 1 2 0. Yeah. So it will be also multiply of 3 factorial. So yeah. Okay. So the case will be high. That will be, yeah. So it will be uh 90 into 3 factorial 96 factorial 90, yeah, 90 into 3 factorial 540. So 600 will be answer. Yeah, again I mistake one cases. So thank you. Okay, thank you for make me clear. Okay, so it will be 60 plus 540 equal to 600. Yeah, okay, that is B. Yeah, okay, I think it is understandable. Then yeah, it is a good problem. I think it is a problem from ISI 2021. A matrix is chosen at random from the set of 2 cross 2 matrices with elements 0 and 1, 0 or 1 only. So the probability that the determinant of the chosen matrix is non-zero. So let us think A is a matrix A, B, C, D. So determinant A, determinant is non-zero. Yeah. So that means AB not equal to CD. Now see all the elements either 0 or 1. So A, B, C, D either 0 or 1. Okay. So AB can be 0 or 1 or CD also 0 or 1. Okay. So because key ABCD either 0 or 1. So if we multiply, we get only 0 or 1. Binary case. So we have to probability that AB not equal to CD. So how we can find AB not equal to CD? That means if AB is 0, CD is 1 plus AB1, CD 0. Okay. So AB 0 that means A0, B1, CD1 means C1, D1 plus AB0 means key at least A or B 0. So A0, B1, A1, B0, C1, D1 will be constant thing plus probability all are 0, A0, B0, C1, D1 plus again AB1, CD0. It is equivalent case now. So what will be the probability? We just multiply with this into 2. Okay. So because this is equivalent case now, AB0 CD1 and AB1 CD0. This is equivalent cases. Okay. So wait. Okay. So the probability will be now see A0, B1, C1, D1. We have 4 entries A, B, C, D, and A, B, C, D can be 0 or 1. So A can fill by 2 elements. So 2. For B there is also 2 element. For C there is also 2 element. For D also there is 2 element. So for A, B, C, D we can choose from 0 or 1. So there is 2 elements. So we choose from 2. That is 2. For B 2, C 2, and for D also it is 2. So if we multiply this thing, it will be 8. So total so probability will be
Sir, it will be 16.
oh sorry, yeah, 16. Thank you. Today I do many silly mistakes. Okay, 16. Yeah, 16. Then it will be 3 into 2, 6 cases. So 6 by 16. Okay. If there is any answer, 3 by 8. Yeah, this will be answer. See, A0, B1, C1, D1, it is one case. A1, B0, C1, D1 is another case. A0, B0, C1, D1 another case. And also it will be repeated. So into 2. So 6 cases and total number of cases is 2 to the power 4. That is 16. Okay. Now, yeah, this is a good problem. 3 numbers are chosen at random from 1 to 0 without replacement. That is say in the previous problem, that is without replacement. SRSW word. What is the probability that the minimum of the chosen number is 3 or their maximum is 7? So Okay, so probability that minimum. Okay, one more thing. You all know the Poincare theorem. That is this formula: probability A union B equal to probability A plus probability B minus probability A intersection B. All you know. Either I cannot solve this problem for you. Say anyone? Do you know this formula?
Yes, sir.
Okay, thanks. So then it is easy for you to understand. So minimum of the chosen number is 3 or maximum of the chosen number is 7. Okay, that means or means union. Okay, it is everywhere. At least, at least minimum of 3 or minimum of 7. So minimum of 3, probability minimum number is 3 plus probability, that means union, plus probability maximum is 7 minus probability minimum 3, and means intersection, that is this thing, A intersection B, and max is 7. Now there is one tricky thing, that is, see, minimum is 3. That means we know that minimum number is 3. It is actually fixed. Okay, so from 4 to 10 there are 7 numbers. So we just have to choose from 7 C2, because we have to choose two numbers from 7 by 7 C2 ways. But in the denominator it will be 10 C3, because we choose without replacement 3 numbers from the 10 numbers. It is also, discrete uniform distribution, what I say, that you can study later when you study the probability distribution, then discrete probability distribution. So okay, whatever. So this is actually the main thing. So 3 is fixed, then the two numbers are chosen from 4 to 10. There are 7 numbers, so 7C2 plus 10C3. The maximum number is 7, so there is 6 numbers here. So from 6 we'll choose 2. Now there is minimum 3 and maximum 7. That means 3, 4, 5, 6, 7. So 3 and 7 are chosen because minimum 3 and maximum 7, it is given, it is fixed. So from 3 we just have to choose one. This is actually our answer. How we can solve this thing? Wait. 10C3, 7C2 plus 6C2 minus 3C1. 7C2 means 7 factorial. 7 factorial, 5 factorial, 2 factorial. 62 means I think 15. 6 factorial, 2 factorial, 4. 6, 5, 4, 6 factorial, 2 factorial, 4 factorial, minus 3, 10 factorial, 3 factorial, 7 factorial. Check my calculation if I do any mistake. 6C, 6, 7, 6, 5 factorial cut off, 2 plus 6, 5, 2 minus 3 by 10, 9, 8, 6. So it will be 21 plus, yeah, 15 minus 3 by, yeah, 5, 3, 15, 8, 120, 12, 11 by 14, 11 by 40. Yeah, okay, this is the answer. Okay, you can try this problem. It is also easy. I give a hint to you because all the problem I cannot solve in one class. Uh, you understand this thing because I have to explain all the thing. No? So okay, for this you just go from this thing. The minimum value of a and b when a b positive integer will be 1. So a plus b, minimum value of a plus b will be 2. Okay, so from 2, 3, 4 up to you have to find, you have to go to 60. So you have to just find for 2 which is the possible cases of AB. So it will be like 1, 1. For 3 it will be 1, 2, 2, 1, these two cases. For 4 you can see it will be 1, 3, 3, 1. Sorry. Oof. 1, 3, 3, 1, 2, 2. So you can see a pattern now. For 2 there is case is, there is number of cases 1. For 3 the number of cases 2. For 4 the number of cases 3. So see there is a pattern 1, 2, 3 up to this thing. So when you see the number is 2, then the number of pair is 1. So that it means 2 minus 1. For 3 it is 2. For 4 it is 3. So for 60 it will be 59. So you have to just sum up this thing. Okay. So the answer will be, I think you will understand this thing. For 2 we get one pair 1 1. For 3 you get 1 2 2 1. For 4 1 3 3 1 2 2. You have to see just the pattern of the question, the number of ways. So you see 1 2 3, and if you take 4, 5 you can also see. For 5 the denomination would be 1 4 4 1 2 3 3 2. So 4. Okay. So answer will be, you if you do sum the all cases, the answer will be n into n plus 1 by 2, 59 60 by 2. So I want to give hints why I solve this thing. Okay. So 0 3 9 7 2 3 15 17. Yeah, this thing. Okay. Okay. Then it is easy problem. It is easy. It is okay. I can solve this thing. You will try this, huh? It will be, you can use additive property here. Additive property of combinatorics. Okay. So here see, in this question it is said that two integer m and n are chosen random with replacement from 1 to 9. So m n era, they will be, sorry, they will be follow they will be follow discrete uniform 1, 2 up to 9 independently. Okay, that is it, as this is with replacement. It will not require, I said this, you can check in any statistics book, you get easily this thing. In sample survey, you will read this thing and set this thing priorly. Okay, but it will not require. See, we have to find probability that n square minus n square is even. So m and n, they are integers. Okay, so m n are integers. That means that means m n can be odd or even. So our target is to find m square minus n square will be even. So how we can do this? See, there is only four cases: m odd, n even, m even, n odd, m even, n even, m odd, n odd. So if m even, n odd, then see, you take just one example. Odd means, I mean, 3, and even means you can take 4. So 3 square, 9 minus 16. It is minus 7. That means it's a odd number. Okay. So this will not be the case. Then even odd. Even you can take 6. Odd you can take 5. So 36 minus 25 equal to C 11. It is odd number, not even. So it will be not the case also. For even, you see, you can take 6, you can take 4. So it will be 36 minus 16. So it is 20. It is even number. So another you can take for recheck 2, 2, 2. If we take the same number, so then it will be 0. Or if we take 4, not 4, one I take 4. If I take 8 and 6, 64 minus 36, 28. 28, that is also divisible by, that is also even number. So it is a one case. Then odd. So for odd, also you can see if we take 1, 3, so it will be 1 minus 9 minus 8, it is even. If I take 7, 5, 49 minus 25, 24, it is even. So this is the two cases: even, odd. Okay, you just check by taking small example. It is easy for MCQ. So our required probability will be m even, n even plus m odd, n odd. So m even, n even means, see, here is two entry, m and n. So for m there is n elements. So here we can choose one number from 9. So it is 9. So for n it is also 9. By multiplication theorem it is 81. So it is 81. Now how many numbers are even? 2, 4, 6, 8 are even. So only 4 numbers are even. So 4 into 4 plus it is 81. How many numbers are odd? 1, 3, 5, 7, 9 are odd. So there is 5 numbers. 5 into 5. So 16 plus 25 by 81 equal to 41 by 81. 41 by 81 will be the answer. Okay. Okay. Then it is a functional problem. It is easy actually. I want you will solve this. It is a PSB problem in which year of ISI I don't understand. I don't think remember. I don't remember, but I want to solve this thing. But my Apple Pencil is out of charge. Let let's wait for just 2 minutes. Just 2 minutes break as my Apple Pencil is out of charge. Wait. Okay. Okay. Let us start. Okay. So yeah. See, it is said that it is actually a PSB problem. Um, of 2029, I think. 2029 ISI PSB. So consider all permutation of the integers 1 to 100. In how many of these permutations will the 25 number will be the minimum of the first 25 numbers and the 50th number be the minimum of the first 50 numbers? So how can we think this thing? Again, I want to read this thing. Consider all permutation of the integer 1 to up to 100 integers. In how many ways of this how many of these permutation there are 100 factorial permutation. So how many of these permutation will the 25 number, that means from 100 factorial permutation there is one permutation where 25th number be the minimum of the first 25 and 50th number is the minimum of the first 50 numbers. Think what is said. You first this type of problem where you have to say the 100 integer. That means you must draw a line or real line or integer line. You must draw. Otherwise, you cannot understand the problem. Okay. Otherwise, you cannot understand the problem. So it is think. It is our integer line where 1 to 100, where a permutation of 100 factorial permutation, I take one permutation. Okay. And there it is like 1 to up to that thing, and not from starting from 1 to not necessarily, but you think in this way. So for in this permutation the 25th number be the minimum. That means it is fixed. 25th number is fixed, then you have to fix, otherwise you cannot solve the problem, because it is said that we have to find such permutation where 25th number be the minimum of the first 25 and the 50th number be the minimum of the first 50 numbers. So how can we do this thing? Okay, it is very interesting problem. So to do this, first we have to choose 50 numbers from 100 numbers. Okay, the process one, that is choose 50 numbers from 100 numbers. In 100 see 50 ways. Okay, now you choose the 50 numbers and you fix the minimum of the 50 number at the 50th position. Okay, you choose the minimum of the 50 numbers in the 50th position. Okay, understand the line. Then you have remaining the 49 numbers. Okay, so there are, now first I have to write fix the minimum of 50 numbers at 50th position. Then we have 49 other numbers which are greater than 50th number. Okay, so from the 49 other number, okay, from the 49 other number, we have to choose the 25 number because we want to fix the 25th minimum number. So to do this, we have to choose, because see, here it is said that we have to fix the minimum of the first 25 number, okay, and the 50th number. We first fix the 50th number, then we have to choose again the 25 numbers from the 49 remaining numbers. So choose 49, sorry, choose 25 numbers from 49 remaining numbers in 49C25 was work. Okay, so then we have to fix the minimum of the 25 number in the 25 position. So fix 20, fix minimum of the 25 numbers at 25th position. Then what we can do? Then see, there is 24 number remaining. Okay, and in this place, that is the 25th number, that is the 50th number, that means here 26th number, here is 49th number. So how many numbers is there? 23, 24. So in this interval, there is also 25, 24, 24 numbers, and we choose 50 numbers now. but the remaining 50 also there na. So we have to permutate also this 50 numbers. So here is also remaining of 50 numbers. We cannot interchange we cannot interchange this with this because we choose first 50 numbers. Okay, I mean key we have to fix the first 50 number na. So because we have to find the number of ways where the 25 number will be the minimum of the first 25 number, and the 50th number will be the minimum of the first 50 number. So we cannot interchange this with this. Okay, this thing must be remembered. Okay, now so it is super easy. So total number of ways will be total number of ways will be 100 C50, then 49 C25, then 24 factorial into 24 factorial. This is 24 factorial here. Also here 24 numbers. So it will also 24 factorial. And there is 50 factorial. It will be the answer. If I solve 100 factorial, 50 factorial, 50 factorial, 49 factorial, 25 factorial, 24 factorial, 24 factorial into 24, sorry, 24 factorial, 50 factorial. So answer will be 50 factorial, 50 factorial, 24, 24, 100 factorial by 50 into 25. It will be the answer. 25, 25 for 4 factorial will be cut off, and 50 factorial means 50 into 49 factorial. So 49 factorial, 49 factorial cut off. So this will be the answer. Okay. So I say once again, first choose 50 numbers from 100 numbers in 100 C 50 ways. Then process 2, fix the 50th number, the minimum of the 50 number at the 50th place. Then choose 25 numbers from remaining 49 numbers in 49 C25 OS. Then fix the minimum of the 25 numbers in the 25 place. Then there is remaining of 24 number, there is remaining of 24 numbers, and there is remaining of 50 numbers. But you have to multiply this thing by multiplication theorem of combinatorics. Okay, so you must have to solve uh, the problems from previous years of ISI and JAM problems, ISI MSTAT and JAM MS, or ISI not only MSTAT, in other exams like MTech exam, huh? Like JRF problems, and there is JRF in JRF, ISI JRF statistics, QROR, so MTech QROR. So there are many problem of combinatorics and classical probability problem. You must solve those things, and you must read one book, that is Sheldon Ross first chapter. Okay, not the total book for this thing. You 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 can try the problems of that book and another book also, but you must I suggest you to read the first chapter of Sheldon Ross, Introduction to Probability, and solve the first solve the examples. Okay, because the examples of that book is very important to understand your to make your concept clear, okay, in the combinatorics and the classical probability. Okay, and then you can try the problems of the exercise. Okay. Okay, because the theoretical part, not the theoretical part, actually the book is good for its examples. Exercise is also good, but in the example many problems are solved, and if you see the solution process or think the solution process, then you can easily understand the topic. And the total book, the Sheldon-Ross total book of the introduction of probability, total book is also very good. You can try to read the whole book, but you can try to study the whole book. But firstly, for commentaries and probability, you must read the first chapter. Okay, and I think this book is very helpful for you for whole probability. The total probability part is very much uh, very much easily explained in that book. Okay, so it's my suggestion to you. Okay, so then, okay, I will end the class by solving last two problems, that is the 19 and 20. Okay, so a packet contains 10 distinguishable firecrackers, out of which 4 are defective. Okay, so that means 6 goods. And if three firecrackers are drawn at random without replacement from the packet, then the probability that all 3 firecrackers are defective. So it is said that it is without replacement, so it is super easy. So what will be the denominator? So we choose 3 firecrackers from 10 distinguishable firecrackers. So different firecrackers. So 10C3. What will be the numerator? Okay. What is our favorable number of case? Then the probability that all 3 firecrackers are defective. So what we choose, the 3 firecrackers all are defective. So no problem. So we have 4 defective firecrackers. So from 4 we choose 3. That is answer. So 4 by 10 factorial, 7 factorial, 3 factorial. So 4, 3 factorial, 7 factorial, 10 factorial. So 10, 9, 8, 6, 4, um, yeah, what I do mistake again. 10, oh, yeah, no, I don't do any mistake here, I think. 3, 3, yeah, 1 by 30, this thing. Okay, so it is without replacement now. So we have just to choose, don't we have to arrange. So it is just 10C3. We choose 3 element, we choose 3 firecrackers from 10, so it is 10C3. Okay, the last problem. So you know the meaning of IID. I think some of you know, or you can know, I think. You know, anyone?
Yes, sir.
Okay, so I think you know it is independent and identical. So where there is no meaning of independent, it is actually an extra thing in the question. We just use the criteria of identical thing. Okay, so see, what is the case in the probability? What is the case? The case is x3 less than x2 less than maximum of x1, x4. So it will be like x3 less than x2. This is fixed thing, na? x3 less than x2. Then maximum of x1, x4. So think if maximum is x1, then x1 is greater than x4. So this place is filled by x4. Sorry, wait. Maximum x1, x4. Let us assume maximum is x1. So here is x1. Now x1 is greater than x4. So x4 must be less than x1. So x4 may be here, maybe here, maybe here. Think x4 is less than x1. So x4 may be placed in here, in between x2 and x1, or in between x3 and x2, or in the front of x3. So there is three place for x4. Okay. Now this is one case, and if it is C, I have to write this thing in this way: x1 less than x3 less than x2. Sorry, x3 no, x4, x3. Yeah, it is number one case. Number two case is very sort of page. Okay, I have to write x1, x2, x4, x3. x3 less than x2 is fixed. Okay, the place of x4 is changed. I think I am I am clear to you this thing. Then x1 less than x1 less than, yeah, x1 less than x2 less than x3 less than x4. So see, one place is here, one place is here, one place is here. The third position, second position, first position. So that three cases. Now if it is case 1, and in case 1 there is the subcase 1, 2, 3. Now the second case is if the maximum is x4, that means x1 less than x4. Okay, so x4 is maximum. Then x3 less than x2 less than x4. So x1 is less than x4. x1 is less than x4. So x1 may be here, maybe here, maybe here. Okay. Similarly, there will be three cases. One is x1, x3, x2, x4. Acha. x3, x1, x2, x4, x3, x2, x x1, x4. Okay, I think, yeah, in the first position, the second position, in the third position. Okay, so total number of cases 6. Okay, so the probability will be 6 by 4 factorial, because see, x1 less than x2 less than x3 less than x4. If I write this thing, it is one case actually. It is one case. So there is actually 4 factorial case now. 4, 3, 2, 1. So it is 4 factorial. So it will be 6 by 24. There is 3 cases. There is 3 cases. So 6 by 24. So sort of pages. Okay. You are understand. Okay. You understand this thing, so no problem. Probability will be 6 by 24. 1 by 4 will be the answer. Okay. Okay. So time is over for this day. Okay. Thank you. I think all I said you will understand, right? Okay. Thanks. Thanks. Okay. Okay. See you at the next class. Okay. Thank you. So I stop the recording. Okay. And you can leave. Okay.